but you cannot start screen. Wait.
Thank you, Anna,
Okay.
again.
Thanks a lot.
Can you all see my screen?
Yes.
And you can see me as well. Okay, nice. So I will start now. So hello, everybody. My name is Rémi Chaput, and I will present the work I made with Amélie Cordier and Alain Mille on explanation. What does it mean for humans, for machines, and for man-machine interactions? So in this work, we broaden the question of explanation to all fields of AI, not limiting to machine learning. We will quickly review the literature, and we will propose to move towards a new user-explained AI model or UX-AI model. So first, a little bit of context. I think it is clear now that there is an important and growing impact of AI applications in society. It is even more so important with machine learning and deep learning, but it is not limited to these fields. And therefore, there is an urgency of research on XAI, which is very well represented by workshops such as this one and the vast amount of literature. In our work, so we claim that there are many works who try to take into account specific audience profiles, such as end users, domain experts, AI researchers, etc. But they mostly do so by pre-constructing explanations and not by constructing an explanation process with the user. And we posit that explanation is really a complex process and which must be co-constructed with the user within the context of the user, their own task, responsibilities, knowledge, their mental model, etc. So, of course, there is a vast amount of research from other communities, such as social sciences. Tim Miller said that in his presentation yesterday. We have many works. Here we will focus on several key points from the work of Robert Hoffman and his colleagues. It's excellent work of Robert Hoffman. First, explaining is a continuous process and is a co-adaptive process. And I think that a good example to show that is the example of the teacher and student, which was used by Freddy, I think, yesterday. When a teacher tries to explain a concept to students, they will first give a first explanation. But after that, the students can ask for clarifications. They can say, okay, I didn't understand this. They can try to reformulate. They can self-explain. And the teacher must try to create other explanations to adapt to the audience. Also, the explanation must be triggered, for example, by an element of surprise. And we should facilitate self-explanation because it helps to understand the behavior of an application. And it also helps to check if the audience really understood your explanation. Explanation is also an exploration process. So we should allow users to interact with the system, to dig deeper, for example. And finally, contrast situations can be explained differently. So now I will quickly review the literature on AI. And as I said previously, not limiting to machine learning. The first example maybe is symbolic-based expert systems, such as logic rules, reasoning, knowledge, or also case-based reasoning. So in these cases, perhaps theoretically, we could provide the reasoning steps of the system to explain why a certain decision was reached. However, there are two main drawbacks. First, the origin and justification of the knowledge which was leveraged to create this decision is not generally available. And secondly, it is difficult to use the traces of the reasoning process for other things than debugging purposes. It is not suited for general audiences such as end users. In machine learning, of course, there are many methods and techniques which were proposed to produce explanations. However, argue that explanation is often an artifact, a product, and not a complete process. For example, a user wants to understand the behavior of an application. The user asks for an explanation. You use one technique, for example, I don't know, a feature importance analysis to produce an explanation. And generally, the process ends here. The user can say, well, can you reformulate? Can you use another technique I did not understand? And of course, we should try to aim for a real process. Also, there are several toolkits to create explanation inside industrial applications, which is really good. But even when those toolkits consider several audiences, they do not allow to construct the explanation with the audience. Other important fields are, for example, robotics and IoT, where you have robots or devices which are designed to interact with human beings, and we have to design them so we can ensure the humans can trust robots. And in the field of Internet of Things, there are many concerns such as safety, security, data privacy, and resilience. But it is much more difficult to explain the systems because there is a complex behavior emerging from interactions between numerous devices and sometimes humans in the loop. So it's difficult to explain. And as a final example, bio-inspired systems allow for complex behaviors through emerging rules, but it is difficult to explain such behaviors. And perhaps one solution would be to try to identify key moments of the behavior, which can also be called critical states, for example. I think this is linked to the presentation of Raimir yesterday. Okay, so now that we have shown that the question of explanation arises in all fields of AI, and that we need a complete process of explanation and not to simply create an explanation element, we propose a new model, a UX AI model. So our rationale for this is that the question arises in any decision support agent, and AI is an opportunity to design and develop a dynamic explanation process, which can be constructed and conducted by the user of the system to explain the behavior of such design support agents. To further illustrate the UX AI model, let me compare between today's situation and tomorrow's situation. So today, researchers build decision models from their knowledge, which we call general models, so GMs. Then designers will use the published GMs to build applied models, AMs, which are specific to a given task. For example, a face recognition, which is based on CNNs proposed by researchers. And finally, users will interact with an application and will then use the embedded apply model in the application. This application can help them take decisions. The interaction traces between the user and the application can provide data that can be used to improve the applied model, but also we can collect this data to build massive data corpuses, which are then used to further improve and build new general models. So tomorrow, with the UX AI model in mind, researchers will not only publish a general model, but also an associated general model of explanation, which we call UX AI GM. And the UX AI GM contains the necessary knowledge to explain the behavior of the application. So here, we need the various methods and techniques proposed in machine learning communities, for example, to create explanations. But when designers integrate the UX AI AM, so applied model, they will also consider the possibility of co-constructing explanations with the user. in addition to, of course, the techniques for producing explanation elements. So when the applied model is deployed, a first UXAI AM is deployed along with the AM. And when the applied model is evolved, the UXAI AM is evolved as well. So the two models are synchronous. And finally, perhaps the level where the difference is the most visible is the user's level. Users will not only have an application, but also an explanation agent. And they can learn to understand the application's behavior by interacting with the explanation agent. For example, let us consider a task, an application with a bank loan. So the user will input its data, and the application will answer, perhaps rejected. Okay, so user will want to know why they were rejected, and the explanation agent will produce a first explanation thanks to one of the techniques, and after that, the user can ask for clarifications, or perhaps even self-explain. So, okay, if I understand well, you mean that my file is rejected because my salary is not high enough. And the explanation agent can try to correct this explanation and will observe the user updating its mental model of the system. Also, the explanation agent can store in its memory the various explanations, both created by itself and by the user, situated in a certain context so that these explanations can be reused in later and similar contexts. As a conclusion, I think that reflecting on UXAI model can help to improve or perhaps solve the following issues. First, there are ethical problems of misuse of AI applications. There are also responsibilities of an user when they use AI applications. For example, the Compass system in the USA, when you use the decision of an AI application to take a decision in real life. And finally, economic consequences of a refusal of use as a precautionary principle. And I would say that UXAI can provide the following. So the user associates a self-explanation with the explanation provided by the agent. The resulting explanation is contextualized with the help of the user for a similar usage situation.
Sorry, Remy.
And finally, just this sentence and I'm done. Excuse me. Finally, contradictions between design logic and usage logic can feed the agent design loop. So sorry for the delay. Thank you for listening. Do you have any questions?
Thank you again for the presentation. We have a question from Pat Langley. He was asking, could you give an example of some reconstructed explanations? All of the work I know focuses on automatically constructed ones. So he was asking if you have any example of some reconstructed explanation.
Not reconstructed, no. You said at early in the talk that most work, the developer puts explanations into the system ahead of time, and that just doesn't sound right to me. Every piece of work I know on explainable AI, the explanation is generated automatically. So what did you mean?
Yeah.
Can you give an example?
Okay, so sorry, perhaps I was too quick on this topic. I said in my presentation that the explanation are pre-constructed. I mean by that, well, you have an idea in mind. For example, you say, okay, I want to explain by using feature importance analysis. So the explanation itself is indeed not in the application when you develop it, but you know what you want to construct. You pre-construct explanations. You say, okay, I will only construct feature analysis or saliency maps, any technique.
Certain types. The developer is going to specify the type of explanations that will be generated. Yes, I agree with that.
That was I was willing to point out. It's we pre-construct explanation. We say, okay, I want specifically
that's not,
this.
That's not pre-constructing the explanation. It's constructing the type of explanation. Explanations are concrete and specific.
Yeah. Well, I would say specifically explanation elements are specific to a given example, a given context.
Well, that would be fun. Yes, but
my explanation is a whole process. So, but yeah, you're right. An explanation element is constructed at runtime by the application, of course.
No, the total explanation is generated at runtime. The elements are always given in advance. Even, I mean, so even in a neural net, you specify the network structure, and that is going to play the role of, at least partially, the role of the knowledge that's used in building the explanation later. Let's take this offline. I just want to clarify that
we can continue this discussion and work chat. Thank you. Thank you very much.
Thank you, Rami. I invite Georgie to share his screen as soon as Rami. Thank you.
Is it okay?
Yes.
Okay, so should I start? Okay, so thank you. So I would like to talk about a proposal for a systematic study of an approach to explainability. And this is joint work with Harish Naik, who is also here at the workshop. So the assumption is that the explanation type, which is the user considers to be relevant, is specified by the user. This is the assumption that we would like to investigate. And of course, the first reaction one has when you hear this, that this assumption does not hold in general. And of course, this is true. But what we hope that it is feasible in some important contexts, for example, in domains where the user, the professional, can be expected to have some idea of what kind of explanation is expected, for example, in science, medicine, and in legal forensic applications. And for example, when one reads survey papers about deep learning in biology and medicine, then usually already in the abstract or in the introduction or the conclusion, one sees that there is a big need for interpretability in the use of deep learning in those fields. And as in this quotation, it also even mentioned that the explanation should go beyond linking the output to particular input features. And in particular in biology, there are a lot of different types of explanations, and it is a separate field of study. This book is, for example, a collection of papers which just discusses what are the different types of explanations in biology. So I just give two quick examples of what kind of explanations are we thinking of. So one is Bayesian networks, where the explanations are arguments. And so Bayesian networks are considered interpretable when one talks about dependencies between the variables. But if one thinks about inference, like in a medical application, deducing a conclusion, a diagnosis based on symptoms, then inference is a complicated probabilistic calculation, and physicians don't like probabilistic calculation anyway. So what a natural type of explanation is to give some argument which could display perhaps the pros and the cons of the various decisions. And so this paper by Timmer and I'll give such an algorithm and produce an argumentation. And so argumentation here, I mean, in the formal sense, argumentation theory is a big field in knowledge representation. The other example would be graph neural networks, where classification of molecules is one of the applications of this approach. And so, for example, this paper, Ying et al. Gives the GNN explainer method, which given an input graph, a molecule finds a small subgraph of the graph, which has the maximal mutual information with the classification. And so this picture from their paper gives examples of what kind of explanations they find and other methods. And so the framework can be summarized by this diagram, where we have an input X, we have a network N, which produces output f of X. And what we would like to develop is an explainer module, which will develop an explanation based on N and X. And now the main part of the model is this R, the arrow R, which is intended to be the relevance relation, which specifies that what should be the way the explanation explains the classification. So you can think of R as standing for reasoning, but would emphasize that it is not necessarily reasoning. Like in the previous example, argumentation maybe can be considered to be some kind of non-standard reasoning, but subgraph relation and other relations are not typically considered to be reasoning. So that will be the part of the model around which everything else is built. So we assume that this R is given first. And so this, of course, is an oversimplification, this model. So for example, it can be the case that the user has only an approximate specification, like they want argumentation, but then what kind of argumentation would be useful specifically? That could involve interaction with the user, elicitation techniques, etc. The very important part is that in these applications, explicit background knowledge seems to be useful, and there are ground truth is available in several cases. And I don't want to go into the details, but for example, graph neural networks could be an important example where, based on the kind of explanation required, the designer, the algorithm designer, actually would design the model, the learning model as well, in order to be able to extract the appropriate type of explanation from it. And so I would like to connect two other topics into the mix of areas which are related to explainability, which were not discussed yesterday. So one is knowledge representation, and the other, which I won't discuss in detail, is theoretical computer science. But one way to approach this kind of explanation is that as the user is specifying the kind of explanation required, there could be a query language in this field, like there are such languages in chemoinformatics, which are used by chemists, biologists to specify queries. And so a kind of explanation required could be a kind of query. So for example, the subgraph example could be one example for that, but one could then use this to communicate many different types of explanations. And for each such specification, that would be an alternative approach to consider learning the interpretable representation directly. And from the point of view of knowledge representation, this could be considered a form of knowledge compilation, and in fact, a kind of approximate knowledge compilation, because in machine learning, the models are supposed to be approximate. And there is a role here to study synthetic data explanations, which is actually done in graph neural networks, but not in a systematic manner. And so another angle on this approach is that interpretability, we all agree that it is a hard problem. And one could argue that one source of the difficulty is that we actually try to solve two hard problems at the same time. One is opening a black box, and the other is to communicate the result of this opening in a comprehensible language. And so here, we assume that this language is given in advance, and this could perhaps make life a little bit easier. And so in the last maybe 2 minutes, I would like to give another motivation for this approach, and this comes from philosophy of science, in particular from Van Frassen, who wrote the book Scientific Image already in 1980, where he has a pragmatic theory of explanations, and he defines explanations as answers to why questions in a contrastive form in the context of a relevance relation. And so already yesterday, we heard several times about why questions and contrastive form. And so here we make a connection to the other parts of Van Frassen's definition, the context and the relevance relation. And so just one sentence about Van Frassen is, this is called an anti-realist philosophy of science, where theories are required to be empirically adequate, as opposed to the realist philosophy of science, they are required to be true. And the last,
okay.
Yeah, I just put up the last slide, is the issue of prediction without explanation, which is also connected to this method. And I stop here. Thank you very much.
Thank you, Georgie. Do we have any question? Do you have any question for Georgie Turan? Okay, then I will ask. Oh, okay, you have. Go ahead. Go ahead.
Sure. Thank you. So yes, it sounded as though you're assuming that the elements of the explanation are produced by machine learning. Can they not be put in by hand? There's all the work on explainable planning where the knowledge elements are put in by the system developer, and then those are used to build the explanation. Does that not count?
So I consider this just from the point of view of explainability for machine learning. So there is a machine learning task. The biologist would like to learn the classification of molecules with respect to a certain property, and then the knowledge is applied to specify what kind of explanation is needed and what kind of background knowledge and other components.
Okay, I guess I must have missed that in your title. Thank you.
Okay. Any other question? No? Okay, then I will ask a very quick one, although I think it's not really quick. It's more about the evaluation methods. Like, it seems that for you, it's enough if we have a formal evaluation of the explanation. But I was wondering if you consider other way to evaluate the explanation, and tell me if I understood correctly.
Well, so from the point of view of producing an explanation and evaluating an explanation, I we don't intend any difference from the standard methods. This is just to set up the framework for what kind of explanation do we want to produce. Like how do you evaluate the subgraph? That would be the same kind of question of how do you evaluate salience.
Yes, so you kind of evaluate in terms of formal like constraints or aspect that you consider being informative for the explanation, and then later work would look at how to evaluate that in other contexts, right?
Yeah.
Okay. I will now give the word to Shane Miller, and please, Shane, feel free to share your screen.
All right, I can't share it right now.
Georgie, can you please stop sharing your screen?
Sorry.
All right.
How do I do that? Sorry, just 1 second. I think I will just have to leave. Yeah.
All right. Thank you. So this work has been sponsored by DARPA under the XAI program, and its genesis really is we've in several years of talking to our program manager, he kept on asking for the nuggets. Tell us the nuggets for the human side, the psychology of explanation. And we've collected these over time, and this is our attempt to try to put them together into sort of a document that covers all of the nuggets of the psychology of human-centered explanation. So what it ends up being is a bunch of tables and lists, which does not make for a very good presentation. So I'm going to show you some of the tables. I'm not going to talk about them in detail, but I'll make some comments about them, especially in regard to this notion of explainable agency, which is the topic of this workshop. So the first, I'm going to talk about 3 main areas of this human-centered approach in terms of measurement, architectures of explanation, and properties of explanation. And then a couple tools or approaches that might help standard XAI developers bring in the human side into the development process. So this is sort of the stereotype of how we see a lot of XAI development happening. People start with an AI system and then they try to think about an algorithm that explains it based on some criteria of goodness. And then maybe they test whether it helps. Sometimes it works the other way around. You start in the middle, you have a algorithm, and then you find an AI system or a problem to work it on, and then maybe you test it. And the basic notion of a human-centered approach is, what if we reverse this sort of and started with the problem? And we heard a lot of great discussion about this yesterday, about in order to make a tool that solves a problem, we should know what the problem is, find the problem when a person is working with an AI, determine how to help them solve that problem better or do that job better, and build that as the explanation, and then determine whether it works. XAI is about and for humans, right? But this probably is, a lot of people in the audience are looking at this and said, well, I never do that. And I understand that, because this is useful if you're trying to build a tool that's going to be fielded, that's going to have customers and users. And there's all types of examples of when people fail to do this, the tool fails. But many of you are not in that mode. You're trying to evaluate an algorithm. And so why should you care? So sort of the idea of this presentation is maybe there's some principles that we can take that are well understood, that have been studied for years, that are known to work, and at least in the sort of algorithmic focused design process, one can try to consider those and try to move that closer to what the needs of humans are in order to address sort of the explanation needs of humans. These come so what we're going to talk about come in three areas: knowing what to measure, knowing how to build systems that explain, and knowing how to best create particular explanations. The main principle is one I call sort of the golden rule of XAI. And I think this is like the most important thing, that all explanation is self-explanation, or like explain unto others as you would have them explain unto themselves. What we mean by this is that I don't care what you put onto the AI system, a person has to understand it and has to change them. So the goal should be to try to empower users to create their own understandings and make their own discoveries, and understand how an algorithm or a display or a visualization helps that. So the first area we've made some contributions to that we talk about is in measurement. And this is something that Tim Miller talked about yesterday, and he gave us a nice shout out. Our approach to measurement is based basically on this flow diagram here, which is about sort of a cognitive process of explanation, that an explanation should impact the user's mental model, which then will help them perform better. As a consequence of this, they might have subjective feelings of trust and satisfaction because of it. So this is the basic notion. Now, when we think about the user's mental model, if you're talking about explainable agency, that user's mental model is basically like a theory of mind. You've got an idea of what this agent is doing. And even for simple things, like even for a classifier, we have a mental model of what this agent is performing. And what a typical base approach would be for humans is to assume it behaves like we do. Assume it does cognitive work like we do. This is something that I've called cognitive anthropomorphism. And this often is a mistake, right? People mistakenly believe that an AI will work like they do. And so this might be a source of where you need to explain things, that no, it doesn't work like this, it works in some other way. We've identified these are sort of the areas of measurement domains. And one area that hasn't been addressed a lot is this notion of licensure that David Tate proposed. And this is about, I think, especially useful for when we're talking about agency, because we're giving permission for something to do things. And this is sort of pre-measurement. How can we measure and understand whether we should give permission for agents to do things, especially when those agents might change over time? A second area that we've looked at and comes from what we might call an explanation architecture. How do you build a whole system that does explanation? And I think that in this community, this hasn't been explored fully, but maybe it should be, because a lot of these lessons come from people that were writing at the end of the first XAI boom. And they said, well, our systems all failed the first time, and then we finally got them right, and this is why we got them right. And so there's a lot of papers out there from the late 80s and early 90s that are saying these things. We need user models. We need to understand context, relevance. We need to give explanations at the right time, and things like this. So this is not about sort of how to build an explanation, but it's how to provide a system that explains to a user. I mean, I think if you incorporate all of these things, or even some of them, you really start getting to this notion of agency in explanation, that if your system knows what the user knows and knows what they're doing and knows what to give them to help them understand, there's sort of like an agency there that should be taken advantage of. But I think this level of architecture really looks a lot more like intelligent tutoring than it does information visualization, whereas most of XAI seems to be almost like information visualization. This is a level of architecture. We've also pored over the literature and found a lot of, this is sort of a taxonomy of types of explanation, but from the human side, there's a lot of similar taxonomies out there that might be more about the algorithmic side that look quite similar. But these are things that come from cognitive systems engineering, XAI, and other human factors domains, about ways that are useful to help people understand the logic of a system. And I think one that seems really interesting and has some connections to other things that have been presented in this workshop is about self and other explanation and critique. So as I said earlier, what we want is the user to explain for themselves, but we could encourage that. Like just putting a chatbot on an AI is not an explanation, but if the chatbot can encourage a person to explain to them, parrot back what they're explaining, have them understand the explaining, and especially critique their explanation to find out where the holes are. This could be really powerful. And I don't know, I haven't seen anyone recently doing critic, but we've used it in human factors for planning. And I think Barry Silverman did work on this maybe in around 1990 and building critics that help people understand things better. So there is precedent here that really could be explored really well when you start thinking about agency and explanation. So that all of these tables are focused on poring over the literature and finding systematic things from sort of the human factors perspective that can help support explanation. And based on this, we kind of put together a set of rants or principles. I'm not going to talk about each one of these, but all of these are more about practical and justifiable principles for design. So things like the work and the context matter, that we should be building explanatory systems, that explanation is not just about transparency, that you have to know what you're measuring, that you might actually benefit by combining multiple measures. So these are some of the things, and this is more like an advertisement for you to read the paper than to give you all the information in the paper, because this is a relatively short talk. This approach has led to a few tools and sort of things that might help in the design of XAI from sort of an XAI developer who isn't familiar with the human side. And one of them is something we call the self-explanation scorecard. And this is really created by Gary Klein. And the idea is, well, if what people need to do to understand a system is self-explain, let's look at the types of things that help support their self-explanation. And so this is sort of a taxonomy of self-explanation. And it's not like a guarantee that if you have a function that's at a higher level, it provides better self-explanation, but this is sort of more involved and more complex self-explanation. But as you see, so what we think you could use it for is, if you look at your own system, you could say, well, I have this part at level 2 and this part at level 4, but actually I'm not doing anything about level 6. Maybe I should be, or why aren't I? And you can see as you go higher and higher, you really get things like diagnosis of failures that are about the logic of the system that might really require causal reasoning and some type of agency to help do this explanation. There we go. So the last thing I just want to discuss, this is sort of a teaser for other work. A lot of these things are not really about the algorithms, but they are about what the people need. And we've been exploring a number of approaches that are sort of low-level algorithms, but still support the explanation. Some things like cognitive tutorials to provide global explanations. Collaborative XAI, replace the algorithms with other people telling you how things work. And a discovery platform to allow you to explore patterns and contrasts. And so we're really excited about this, but I'm not going to talk about it anymore. And I think I've got 2 minutes left for any questions.
Yes.
Or comments.
Do you have any question? Is there any question?
Sure, I'll jump in. So Shane, thanks very much. Nice presentation and good advertisement. Concerning the self-explanation scorecard, could we have used this for distinguishing, grouping different presentations at this workshop?
Could we have? Is that what you said?
Yes. Well, could we as the co-chairs have used this? Could those in the future workshops use this kind of scorecard to?
Yeah. So we have used it sitting down with individual teams building systems and try to use it for evaluating that to see where they stand. And right now we've got a few people who are looking at papers to see if we can find ways of coding. It's not clear that this is that easy to do. You might actually need to be the developer in order to code it this way. I mean, there's a lot of taxonomies out there. I think this would be a useful one if you are interested in grouping together things related to sort of the human side of self-explanation.
That makes sense. Thank you.
Okay, so thank you again, Shane. If you have any other question, please feel free to add them in the Rocket chat. I invite Edward to share his screen. Thank you. Great, you can start if you want.
All right, great. So thank you all for the opportunity to come speak with you. My name is Edward Kim, and this work was done with Andrew O'Brien from Drexel, Connor Onweller, and Kathleen McCoy from University of Delaware. The work we're going to present is the Interpretable Dictionary in Sparse Coding. And I am from the computer vision community. This is my sort of first foray into interpretable and explainable AI. So very open to any comments and critiques. Okay, so let's begin here. All right, so I wanted to begin with two scenarios. This first scenario, we'll call it the scenario of a million coaches. And the problem here to illustrate is the noise and lack of communication. All right, so let's just say that this is you're this boxer, and you're just going about your, living in the world, you're trying to survive, and, stimuli might be trying to hurt you or that sort of thing. And your brain here is your coach. It's gonna try to protect you from any harm. But we're gonna say, what your brain is not just as one entity, but it's a million different selective entities, right? So some of them may be specialize in helping you in certain different tasks, maybe in the attack or the defense or that sort of thing. And so having a million coaches, maybe that's a good thing. They're all sort of specialized in different ways. But the problem here is if they all start talking to you all at once. All right, so yes, they're specialized. They're not communicating with each other. They all have their own agendas, and it just becomes way too noisy in this situation. Now, contrast this with a different scenario is when all of the coaches, they begin to talk to each other and they say, you know what, at this very moment, what needs to happen is this one person needs to tell you what to do. Okay, so that's the first scenario. And I want to talk about a second scenario. This is, I'll call this the blame game or the scenario of a million babies. Okay, so let's just say that you are a lucky parent of a million children and you walk into your living room and you see a broken window. And then so you say to them, hey, which one of you broke this window? And so they all sort of look at each other and they all raise their hands. They're like, oh yeah, it was me. I take the blame for this. And some of them, maybe some of them are sort of less enthusiastic than the other ones, but in the end, they're all sort of shouting at you. And then now your partner comes in to the room and says, hey, what happened here? Can you explain the situation? And you say, well, I'm not really sure. Everyone's sort of yelling at me all at the same time. All right, now contrast this with a scenario here where now all of your children, they sort of look at each other and they start communicating with each other. So they're talking, they're saying, oh, maybe it was me, maybe. And then one person, let's say Connor, says, you know what, everyone, you don't take the blame for this. I was the one who broke the window. And then your partner comes in and you say, and they ask you, well, what happened here? And it's very clear. You can say, oh yeah, you know what, Connor's the one who broke the window. All right, so sort of keep these scenarios in our mind. And I want to say that this is kind of a metaphor for many different things, but in sort of this biological perception, this could be a metaphor for something called efficient coding. All right, so now we're going to say that we have, we're talking about vision here. Our retina is going to send back a million different signals, a million fibers connecting the retina to the primary visual cortex. And In fact, in primary visual cortex, we can say that it actually does dimensionality expansion. There's maybe 2 orders of magnitude more neurons here in we'll call V1 primary visual cortex. And so they're all sort of trying to efficiently represent the visual information that you're seeing. And so what's going to happen is that these neurons in visual cortex, they're going to become very selective to certain stimuli. All right, and there's good reasons for this biologically, metabolically. You don't want your all of the neurons in your brain firing all at once. You can't hear over all that noise, and you'd have to. So it's very energy inefficient. You'd have to eat like 20 different meals a day. But what they found in the early 60s with work of Hubel and Wiesel, as they looked in sort of the cat neurons in V1, they saw that these neurons are very selective to certain different stimuli. And so in this case, what we're seeing is a neuron is selective to this diagonal looking stimuli and not to others. And so this was sort of the prevalent view, but then in 2019, work from the Allen Institute and AI, they looked at the visual neurons of a mouse cortex, and they saw, well, it doesn't actually work like that in all cases. And so what they were finding is that, yes, neurons in V1 are selective to certain sort of stimuli, natural stimuli that happen in the world, but sometimes they're completely silent. And so the hypothesis is that, well, it's not just an input, sort of a feed-forward input signal that's driving these neurons. There's actually many feedback. In some cases, there's even 10 times more feedback connections, sort of modulating the activity of these neurons. There's also, importantly, there's lateral connections within the layer. Okay, so these lateral connections are going to inhibit other neurons from firing if they are the neuron that can best represent the input stimulus. Okay. Okay, and then also there's there's this theory in efficient coding that the elements must be sort of tuned to the natural signals of their environment. So, in sort of the natural statistics of images around us and video are these edge detectors. So that's what sort of we get attuned to. And if you know about computer vision and convolutional neural networks, that's sort of what emerges as these features. Okay, so coming now to sort of the explainable AI side of things, there's some work from Cynthia Rudin. She calls this the double trouble situation, where what people do, at least in computer vision, it's pretty common that you have this very complex black box model, and it's sort of not explainable. So what you do is you build these explainable modules on top. And the problem is there cannot be complete fidelity between the explainable module and the black box model itself, because if there were complete perfect fidelity, you could throw away the black box model. So they must sort of fundamentally disagree at some point, and therefore you can't trust these explanations. And so what's the solution behind this? Well, maybe we shouldn't be doing black box modeling and sort of start from, I guess, kind of from scratch and look at, well, if we start with interpretable elements, maybe then we can get an interpretable model. And so that's kind of the view that we're taking in this work. And if you're not familiar with what a typical CNN would do, you have some input, and then we have these image filters, and it's just sort of this sort of matrix vector multiplication here, dot product, and you can see these would be the activations of this input convolved with these image filters. And it just so happens that filter 2 here is almost identical to the input. You can see that its activation would be very high, whereas they sort of act independently from each other. Okay, so coming to the sparse coding model, sparse coding is a representation learning algorithm. I'm not going to go too much into this here, but the basic idea is I have an input stimulus and I want to best represent this input stimulus by a combination of a dictionary element and its coefficients. And you can think of this almost as the image filters of the CNN. And I just want to use a very few linear combination of them. And so here's the sparsity penalty to make sure that most of these coefficients are 0. Okay, so then if we were to visualize what the sparse coding model looks like in comparison to a CNN, what you have is similar thing. So we have the image filters just like before. We'll call them dictionary elements. But here's the interesting thing. So if filter 2 is sort of identical to the input, what's going to happen is in the sparse coding model, it's going to say, look, I'm the one who can best represent the input. I can do the best reconstruction. Therefore, everybody else needs to be quiet. All right, so this is sort of what you would see. I'm the generator. I'm the cause of this input. I'll take the activation. Everyone else should be 0. Okay, now when we come to learning a dictionary, I'm not going to go into the details, but we can do a feed-forward autoencoder, and we can do the same structure with a sparse coding model, and they'll come up with different image filters, different dictionary elements. The fact that there's this sparsity within sparse coding actually makes these dictionary elements much more visually appealing, I would say. And there's actually been a lot of work from Vincent and La Rochelle about how just a standard autoencoder can't learn good features from data. You have to use denoising, you have to push it back to the manifold, that sort of thing, where you don't have these problems in sparse coding. Okay, I'm quickly running out of time, but I want to give you some results here. So this is a filter from a CNN. This is a dictionary element from a sparse coding model. And what you're seeing here in the blue is that everything in the CNN is active. All right, so this is kind of active, this is very active, but it's active all over the place. Here in a sparse coding model, you can see it's sort of very selective as to where it becomes active. You might be saying, well, you know, this seems to be active in all the right places, but I would argue that it's just active anywhere there's high frequency elements. So you can see in a CNN, I mean, there's activity all over the place. And it kind of reminds me of this work that was done where they were using the backpropagation gradients to see what is this sort of the heat map on why this is being classified as a Siberian husky. And it's a sort of the same heat map for why this could be a transverse flute. All right. Whereas in the sparse coding model, what you have is, again, very selective activity in different places. This one kind of looks like sort of multi-line text or large sort of fonts that you can see that they become active there. This one's a white space dictionary element, and you can see it's only active where there's white space. All right. Oh, and then here we have just an image patch. And I just want to show you that the activity of the sparse coding dictionaries, it's very sparse. There's 5 elements here, less than 5% are active, whereas it's 100% active in a CNN. You can look at the paper for some more details. Okay, so I'm just going to jump to one last point here, and the question might be, well, are these good for anything? And the answer is yes. So Sheng Lundquist, in his PhD thesis, he defended recently, looked at convolutional CNNs. These are in a supervised setting and on a card detection data set. And you can see that a sparse, unsupervised learning algorithm, like the one we're talking about, can actually get even better accuracy in this case over filters learned in the convolutional sense. Okay, so they are good for something. So in conclusion, sparsity, I believe, is a key component to interpretability. Sparse coding, this algorithm yields a sparse selective representations that are more interpretable than your standard CNNs. They're biologically plausible. I didn't really go into this, but they are. And you don't lose out on accuracy if you do this unsupervised method. compared to supervised. But there, of course, there are downsides to everything. So it's slow. It's an optimization process. It's not a feed forward process. So you do have some downside. Okay, thank you.
Thank you,
Any
Adam.
questions?
Great. So I think we have a question.
Oh.
Yes.
I got a question. Go ahead, Rosina.
Thanks, David. So hi, thank you for your very good presentation. I have two questions, but I believe that given that it's kind of the first here, not a very common topic in the field, I would like to ask you more generally, as yet another kind of dimensionality reduction approach. If you would compare to attribution methods that have been used to reduce a machine learning method to try to explain it and make it more interpretable, how do you see the sparsity coding algorithm doing this dimensionality? Do you think is it doing more at the feature level? You believe this would be another way of doing feature attribution, or do you think could be perceived more as an instance attribution?
Yeah, that's a great question. And I think the differentiation would come down to the objective function. In most of the time when you see with attribution methods, the sort of the pipeline of the computer vision is a supervised learning. So they have sort of input end-to-end input pixels to class. And then what you do is you sort of back propagate the weights from errors, and then you can sort of see where things were active based upon sort of the class. Whereas when we're talking about the sparse coding method, there is no notion of classification here. It's just trying to best represent the input signal. And so what I'm working on now is showing that even in this unsupervised setting, when we're just learning a good representation, we can still take that representation and put a very simple, maybe linear or even something even simpler population of neurons for classification. And then so given sort of the simple decoding process, that actually might lend itself to even more interpretability.
Thank you.
Okay, we have another question. Do you want to ask? There is a question on chat. What do you think on how this relates to knowledge distillation?
Knowledge distillation. I think I'm going to need a definition of that.
Oh, hey, thank you. So yeah, I asked that question. I just decided to unmute myself. So
okay.
Yeah, so I'm more or less talking about, it's not a different field, but people try to, essentially, for example, distill, they started from distilling networks, but then they started to, essentially simplify the input so that the most important features are distilled. It sounds very similar. What do you think about this relation? It's the relationship between that and your approach.
Yeah, I'm going to guess that in knowledge distillation, we're not talking about images, because in the case of sort of these signals, right? You can't know a priori what to distill from an image. So you'd have to put sort of everything in, and then have an efficient encoder process to. I guess that would sort of be the distillation process. But
yeah, I was mostly talking about like language and knowledge. Knowledge graph things. I know that that's different field, but thanks.
Yeah.
So Jiu, I'm not sure if you're done, but if you're done, I have some questions for Edward as well. So
Go ahead. Yeah.
Okay, so great to see you again. Thanks very much for your paper.
See you.
And I've got a few actually. I'm sure there'd be too many then for just this short time, but I'll follow up with you at our break. This is so. I admit that I'm not sufficiently well read in sparse coding. This can easily, I assume this can be applied well beyond computer vision tasks to support XAI tasks. Is that fair?
I would think so. So anything that I mean, so sparse coding, in essence, can be thought of as almost like a feature selection type of. It's feature selection in some contexts. It could also be sort of this regularization process in other contexts. So I think the main issue here, when most people talk about like regularization of a network, they're talking about the weights of a network. And so, you kind of want to control the weights. Here we're talking about activity regularization, which is something that really needs to be done over sort of this optimization process. And that's sort of why no one likes it, to be honest, because it takes a lot of computation to do just like the inference process. But I think maybe that might be necessary.
You made that message clear in your presentation, and I hope that's not stopping everyone from using something like this. I'm reminded of other processes that have been proposed and published in the literature that talk about combining, say, well, compositionality in general, whether that be for previously trained neural nets to solve a more complex problem or whatever. But is it correct to think about sparse coding as, once you've got the language, to think of it as a compositional technique for problem solving?
Yeah, I would think so. That it's sort of, once you've got these you sort of learn the building blocks of whatever input you have, then it's essentially like trying to use as sort of like the most parsimonious, right? The simplest explanation is the best. Use the fewest of these building blocks. Is that sort of?
Yeah, sure. So are there other limitations that we should be aware of that are preventing people from doing a lot more work on sparse coding for XAI and related tasks? For example, is it more than just optimizing for trying to identify what the language is? Are there additional things that you have had to worry about in your work on in using it?
Yeah, so I think the trendy thing is everything needs to be end to end these days. If I'm going to, I don't want any sort of intermediate steps within my pipeline. I just want to put, input to classification, input to segmentation, input to whatever. And so here, so again, so there's no notion of, you'd have to sort of take the representation and do one sort of step on top of that, which, yeah, at least within computer vision, the moment you say you're not end to end, people sort of shut down and they say, well, why didn't you go end to end?
Got it. Thank you.
Yeah.
Okay, thank you. We have also another question from Tobias. I would say this is the last question we take. Then for all the others, we can use the Rocket Chat. So Tobias, would you like to ask?
Yeah. So thank you for the great presentation. I was just wondering if you know of any applications in reinforcement learning of your sparse coding technique.
Sorry, I lost. Okay, so reinforcement learning in sparse coding. I don't, off the top of my head, know any combination, but I can see again, sort of representation learning is just going to be the first step of most of these pipelines. So if you find a very good, efficient representation, and then you can sort of put goal-based objectives on top of that. So I would imagine it would be compatible.
Yeah, I think so too. That's
Yeah,
why
I like
it's
your work on reinforcement learning, so I have to learn more about it.
Thank you.
Okay, great. So we have now 5 minutes for networking among us. So if you want to like ask questions that you couldn't ask during the session, those are welcome. And then we will have the lunch break. So like last 5 minutes, please, if you have a question, do not hesitate.
Can I ask a quick question about the recordings from yesterday? I was looking on the webpage. Are they not going to be up?
They will be up, but it's very long and it's taking a long time to get it all processed. So if we get this, whenever it's done, we'll share here.
Great, thanks.
Sure.
I've got a generic question that is related to something David and I were talking about at the end of yesterday. So it seems to me that when most of us talk about explanation, whether we're working with handcrafted knowledge bases, as those of us who work on explainable planning, or whether we're talking about learned knowledge, the process of generating explanation has nothing to do with learning. It's a performance task. And somewhere along the way, the machine learning community seems to have forgotten this distinction. Obviously, they measure performance, but in the early days, we back in the 80s, we said, hey, you know, learning is designed to improve performance. And so there was always, you could always run the learned knowledge base, learned expertise with learning turned off, and then use it to do the task you cared about. Now, explanation is not that task. It's a different task. It's explaining how you use the handcrafted or learned knowledge to do the performance task. But explanation itself is a performance mechanism. And there's so much excitement these days, breathless excitement about machine learning, that I think we sometimes forget that. So my take is that, yes, you can talk about explanation of the learned knowledge itself, but that's pretty rare. Most of us don't do that. Mostly we're talking about this as a performance task, and many of the and here's why I'm saying this. The principles for explainable AI or explainable energy may be independent of whether you're doing neural nets or rule-based systems, whether you're using handcrafted knowledge or learned knowledge. And we should all be trying to move beyond that. What do you think?
Someone added.
Did you have anyone particular you want to ask this question to?
No, but anyone who just gave a talk is welcome to respond.
Well, I did not give a talk. I'm just sharing the workshop. Does that count?
Sure.
Thank you. I really like what you're saying, because I have myself done work where I learned explanations using background knowledge for a task.
Did you learned explanations, or you generated explanations?
I've learned explanations because I was working with text. Mm-hmm. So the original task, the task I was trying to explain was done with deep learning. So it was generating vectors and embeddings that I could later use and take advantage in order to really learn explanations. So I particularly have that kind of interest, but it's not easy to find the tasks where there is background knowledge in support of that task, so we could have at least at the supervised level. But I would love to hear about other attempts to do that.
Boy, I'm not sure we're using terms the same way. So to me, the explanation is something that's generated on the fly, and you might conceivably learn the ability to generate explanations, but the generation of explanations is itself a performance task that happens in parallel and over traces of the regular performance system, right? So you have a I mean, whether you're doing neural nets or whether you're doing rule-based systems, you're always going to have an interpreter that uses knowledge or expertise to do a task. Doesn't matter whether that knowledge is built by hand or learned. There's going to be an interpreter. And now you run that on a particular instance of a task, and you get a trace. Could be the activation levels in the neural net. It could be the plan generated by a planner. And then there's a separate process that takes that trace and generates an explanation that we can understand. Now, and I don't hear people talking about things this way, and I wanted to throw out that. Now, what you just said confuses me because I don't know what it means to learn an explanation.
Gary here, can I make a comment?
Please.
So, Pat, I completely agree with what you are saying. That was a little bit the purpose of my presentation too. And I really agree that yeah, this learning model, that's one thing, and then the learned model might have some accuracy, and and normally we try to get the highest possible accuracy there, but then I had the impression that sometimes people actually mix together this sort of model learning phase with the explanation generation task. And I really agree with you that they should be separated. Then it's a different thing, of course, if we speak about user models and learning user models, but that's again, it's not a task again, I think.
If I can just add my 2 cents real quick, Pat. So not surprisingly, I agree with you. The distinction should be made and made more clearly. And that I believe you would say you haven't seen a whole lot of work that is collecting data in terms of a feedback loop from the human to see whether or not the explanations provided were effective, that could be used for purposes of learning to generate better explanations over time.
That's true, although I'm sympathetic with those researchers. That's why I got out of psychology, is because it's too much work. But it's just a conceptual distinction that I think just like in machine learning, it's important to keep distinct the performance mechanism and the learning mechanism. So we should also keep distinct the explanation mechanism and look for commonalities across different representations, across different ways, you know, to general principles of explainable agency.
So I'd be interested if anyone would pop up and say, yes, I am familiar with work on learning explanations as Pat has put forward, because I'm not particularly familiar with a whole lot of work on that topic.
So we had an attempt to learn explanations in form of actually natural language explanations for the ground truth label that are written by humans and given to the model at training time, and then expecting the model to also output this kind of explanations.
Do you mean that the system learned to generate explanations, or they learned explanations?
So they were given the explanations for, let's say, if a self-driving car is stopping, it won't just learn to stop, but it would be told, we stop because it's green light, or because here this other car had priority. And then it's being given in natural language, and the system would also generate such explanations.
So it sounds like your notion of explanation is a very piecemeal one, like a single reason. Much of the work in explanation is compositional in character. That is, you have a number of knowledge elements, you have to put them together to explain something. But there are examples, certainly, where you have a very simple explanatory piece, and that people say, yes, that's an explanation of this thing. And I can see how you could learn those. I find it less likely that the system would learn you wouldn't want to learn a really complex explanation, because the whole advantage of AI is you can put the pieces together automatically to build larger structures at performance time. But yes, thank you. That's a good example. That's a good example of what would count as learning explanations.
So there could be actually multiple arguments in that explanation. And it doesn't have to be just one piece.
Right,
And
but you're not learning the combination. You're learning the pieces, and then at runtime, you would produce all of them, put them together to come up with a more complex explanation. In that case, you wouldn't learn the larger explanatory structure. You would be learning the elements of the explanation.
do you have an example for how that?
Sure. Well, so it sounds like so in my talk later today, I'll be talking about social norms, and so things like stopping at a red light, right? Or in Pittsburgh, you always let the person turning left go before you, and so these are, some of them are laws, some of them are conventions. You could imagine learning these from experience or from instruction, and then you could, when an agent actually drives the car or generates a plan, you can ask it, well, why did you take that route, or why did you stop then? And there's this little old lady walking across the street. She's jaywalking. You have the every legal right to run her over, but no, you shouldn't do that. And so you can learn those social norms, and then you can use those in the explanation of behavior. I think in many cases, when we talk about explanations, they are more complex structures than individual steps, right? Although there will be cases that you say, well, why did you stop here? And the answer is, well, there was this little lady walking across the road. And if you learned that, then arguably it's not learning the explanation, it's learning a generic pattern that is then used to give a specific explanation later at performance time. I'm not trying to be pedantic. I think it's really important to understand, to get our terms clear and to explain what we mean. So I would say you're learning explanatory structures, and then you use them to generate explanatory instances later.
Yeah.
And if I may, the situation that the work that I've done that I was bringing up is one where the task is such that there is a limited number of explanations. And I'm thinking that the social norms are also limited. And basically what my learning step was targeting was to associate the specific circumstances of that task with all the possible explanations, and then identify the one that would be more suitable. So I think the social norms would be something that we could.
Okay, I think we're converging on something. Whether it's right is another question, but I think we agree.
Good.
I think that
Go ahead.
That the explanation problem in machine learning is very restricted compared to what you are talking about. So just take this example, which was mentioned many times, that you give your data to a neural network. Neural network says that you don't get along. And you would like to know why. That's it from the point of view of machine learning explanation. So how does
if just to try and make the mapping, a neural network is a network, right? It's got multiple layers, and in fact, the knowledge or expertise in it is made up of a bunch of components. The structure is specified ahead of time, but the weights are learned. When you use it to say to recognize an object in some image, there is a reasoning chain. You might say it's not reasoning because it's not logic, but it certainly is sort of multi-step inference process. And you could look at each step along that process. You could try and understand what's going on, and arguably this could be viewed as an explanation of why the system thinks there's a cat in this particular part of the image. It feels different because the rhetoric the language of the neural network community is so different from the language of the classic symbolic AI, which is where work on explanation originally occurred. I don't think they're as different as we might at first think.
Well, I think
I hope you realize Georgi is agreeing with you. So
I think this is the 1 billion.
Yes, but I enjoy arguing.
I think this is the $1 billion question, but everybody tries to figure out whether what you say happens or not. Can you view those nodes as doing something meaningful? That's it.
I think we are running out of time, but if you want to continue, like we have a lunch break. After there will be also the talk of Pat, so I hope we will have more time to continue the discussion.
Don't start without me.
See you later.
So everyone, the workshop proceedings are available on the website now. So if you want to check them out, I put the link in both chats.
So Pat, I'm happy to continue the discussion if you'd like.
Yeah, I think that's the value of a workshop, are these informal discussions.
Did Pat's input to you, Rosina, change your view on this?
No. No, I agree. I agree with him. I agree that perfectly. There is no change.
So you talked about learning the content of what the explanation would be. I didn't hear you talk about other aspects such as the process of giving an explanation, or take this further than just the content. So
well, you see, the content might shed. You see, there is this very strong influence of interpretable machine learning in XAI, which is not surprising, of course, but my view of explanation is that first we had humans explaining things to humans, and now and explaining and making decisions and explaining things to other humans. So now we have agents making decisions and sending to humans. To me, from what I've seen in the literature, the explanations are all the delta between what goes from an AI agent to a human, which is a decision, and what a human gives to another human when sharing a decision.
Mm-hmm.
And this delta has been, and that's what Adam is looking at in his dissertation in terms of types of information. That's how some papers in the literature discuss. And there are many, many different types, and those types indicate the types of contents. But what there is a implicit relationship between the contents and a process that led to that context. So for example, counterfactual. Now we have very precise definitions on how to pull a counterfactual from a given type of system in order to produce an explanation. The same way, and there's a relationship between that process and that content. And those relationships, they are all based on the background knowledge of the domains of tasks. And this is why so many authors say that explanations are domain dependent, application dependent, because depending on the task the AI agent executes, the whole, it defines the whole delta, which what the explanation can be.
Mm-hmm. So I see what you're saying when you say delta.
I have a question of what can be the difference between the two versions. you are talking about and what machine learning is talking about. That isn't the difference that how black is the box.
Honestly, I don't think that opening the black box solves the problems, because if it did, the literature in XAI would not be suggesting so many types of information that do not come from inside the black boxes. The black boxes are a simple reduction, a simple modeling of the real world, and what explains the explanations come from the real world, not from inside the black box. That's a very limited view of
That's
XAI.
what you would like to find. So a deep learning network is considered to be an entirely black box where you don't know anything. You don't know whether it has any relation to anything in the real world. And first of all, you would like to find out whether there is any meaning. Then you want to classify pizzas. Does a hidden node correspond to a dinosaur, or does it correspond to anything at all? So when you are talking about explanation, it's not an entirely black box, because you assume that the agent has some kind of structure, some kind of relation to the world. So it's like the playing field is different. That's my feeling.
Well, the data that was fed to the deep learning is raw data, exists. And it's just that because it's so vast, that for us to make any sense of that, we would need to use those black box methods. But the data itself is not black box.
So let me see if I can pick up on this conversation. So I guess the point is that there is the traditional learning task. Let's say it's, for example, it's image recognition. And we have a black box classifier that could be learned from it. And that's spurned a lot of work, or motivated a lot of work with respect to interpretable machine learning. But there are a lot of other tasks involved in terms of determining what information to provide, that is content information to provide to a user, determining how that should be provided. And each one of them can be thought of as being potentially modeled by the agent. Each one of those models could be the target of either hand encoded knowledge or a learning task, so that if we had feedback from the user in terms of what works for them in terms of the content of the explanation or the process by which they interact with the system, that takes it to a whole new level. And these are separate issues pertaining to XAI that arguably have gotten less attention than have those with just trying to, I shouldn't put it down, which those that have been focused on trying to open up that black box. Is that fair, Rosina and Georgi?
To me, the only point of that would be the interpretable machine learning exercise. Still, it would not be really doing what users need.
Can I give some input to this really
please, Gary, go ahead.
Discussion? To me personally, I don't think deep neural networks are any more black than a support vector machine. That's sort of my personal view, because I know neural networks so by heart, so I can guess or understand how a deep neural network works. So in that sense, I think that no matter how black the black box is, we would still, if we can come up with some universal way of providing explanations in different ways, then that's really what we would need. Also, I think you mentioned the word bridge here, or gap. No, delta, I think. I'm not sure if I understood that properly, but I think there's a really huge gap between what the machine learning people are doing here and the social scientists and psychologists. And with the current approaches, we're not really reducing that gap at all, I think.
I mean, I think one of the problems is that the problem is pragmatically framed by the predictive models, right? So, you know, I mentioned the term a one-shot explanation yesterday when Tim was talking, and that's the problem, is that we're faced with, you know, the problem is framed as one in which a model generates a single prediction. That prediction has to be explained and then the user goes home, essentially, you know. and we know that that is not going to be the way it works. You know, that person is going to be sitting down getting a succession of decisions or predictions or classifications, responding to them, building up a view of that model, a
Right.
view of how
So-
that model is being explained, and so on, you know.
So separately, the point is that there's a model of the explanation process that could be the focus of, again, either encoding or learning itself, whereas most learning work has instead been focusing on a distinct performance task that could benefit if it was supported by an explanation process to be able to communicate to the user. And it would be interesting to see some more machine learning work or more work in general, whether involved machine learning, to target that explanation process.
Yeah. I mean, one of the problems here is there's a really bad blame assignment problem too, right? So when the user is interacting on the explanation, one of the things I've argued is that there's sort of three distinct things they can be sort of interacting with respect to. One is the sort of what the model is doing. One is what the explanation is doing. So people have a mental model of the explanation. And then the third thing is the actual domain that the model is operating over. So people have an understanding of the domain that's separate from what the model is doing with the domain, that's separate from the explanation process or strategy that's been used. And so when we see a user saying, I don't like that explanation, it's not clear which of those three things they're responding to. So learning is going to be really hard over those explanations, I think.
You cognize
going to make a comment
problems harder.
On the same thing, actually.
Well, this is
go ahead,
why
Carrie. I'm sorry, Carrie. Go ahead, please.
Yeah,
Carrie, I
go ahead,
was just saying that I was going to make more or less the same comment as Mark. I think it was Racine or some other people too who mentioned this the need for actually explaining using a domain vocabularies. And I think it's also a question of using the right vocabulary for the right user, as well as using the right mechanism for explaining depending on the context, meaning that if my car is going to run over somebody and wants to explain to me why I should choose the, I don't know, the old lady instead of the dog or whatever, then I don't have the time to read 10 lines of text and counterfactuals and so on. I will need something more graphical.
Like stop.
Stop. Or maybe the car fixes the whole situation by itself.
And this is why.
So our final speaker for the two-day workshop, obviously, is Pat Langley. He's the leader of ISLE, the Institute for Study of Learning Expertise. He also has affiliations with Stanford and the Institute for Defense Analysis. I first met Pat back in 1985. By then, he had been working on topics of scientific discovery, and his system named Bacon was quite familiar with people in the machine learning community. Amongst other things, he was the founding editor of Machine Learning Journal, which he started in 85 and was there through 88. By 1991, he had been making contributions on a cognitive architecture that was called Icarus, which continues to be developed today. Interestingly, you can tell from Pat's expansion of the title of Icarus what his sense of humor is. He introduced it to me as intelligent cognitive architectures are us. So by 2005, he was working with Will Bridewell and others on computational discovery of explanatory scientific models. He's had a long history of interest in this topic. In 2012, he was the founding editor of the Advanced Cognitive Systems Journal, a position he holds today, as well as a mover and shaker in terms of the development of the conference, the ACS conference as it's known. And in 2017, he may have coined the term explainable agency, which we borrowed in part for the title of this workshop. That paper can be found in the AAAI proceedings. So with that, Pat, looking forward to your talk.
Well, thank you, David. Hold on, I need to try and find some way to get your pictures out of the way so I can see my slides. Huh, that's not going to happen. Okay, let me try to ignore you. Don't make any funny faces while I'm talking. So thank you again for having me. I wanted to redo my talk completely based on recent conversations I've had with some of you, but there's no time. So I may make a few comments along the way. But thanks to my funders and my colleagues for the ideas that I'm talking about. So we all know that autonomous artifacts are becoming ever more widely used. Self-driving cars, delivery drones, military robots are on the horizon. But before systems like this are really going to gain widespread acceptance or at least trust, they need to not only explain their behavior in understandable terms, which is of course what this workshop is all about, but also follow the laws, the customs, and even the morals of society. In other words, they have to move beyond what we've been calling explainable agency to what I'm going to call justified agency. Here's an example. So suppose Dan is driving his friend Eve to the hospital. She has a ruptured appendix and he's really worried that she might not make it, right? So what does he do? He exceeds the speed limit. He weaves in and out of traffic. He slows down at red lights, but then he goes right through them. He actually, at one point, there's a traffic jam. He goes up on the sidewalk and comes back down again. At the time, along the way, though, he still has control of the car. He doesn't have any collisions, and he gets her to the hospital. Later, after he's gotten her to the emergency room and the cops have pulled him over, he defends his actions. He says, well, Eve's life was in danger, and reaching the hospital was more important than these traffic laws. And in doing that, he has illustrated this notion of justified agency. Just to be clear, the term justified here is not in the sense of a logical justification, which of course any theorem prover does logical justifications. I'm talking about in the legal and moral and ethical sense of say you killing someone in self-defense is justified. Now, you heard me talking about terminology yesterday, and I just want to get some terms on the table and clear it up, at least for the way I use them. In English, there's two senses of the word explanation. One of them is a structure. It could be mental, it could be written, it could be spoken, that clarifies some sort of phenomena or behaviors. For example, we might have a scientific account of the cycles in pulsars, or clarification of how someone made a decision about which home to buy. Okay, that's the structure. But there's also the process or activity of generating that structure. So we say that a scientist or buyer engages in the explanation of pulsar behavior or purchase decision. Okay, so they're both important. And I'll be using both senses in this talk, as many people have in their talks. Usually the meaning is clear from the context. Sometimes it's about the structure itself. Sometimes it's about the activity of building that structure or using that, or we're doing something with that structure. And that's not a big deal. It's worth being clear. But there's another more important and less obvious distinction between two other senses of explanation. And I'm going to introduce some new terms here. The first is what I call interpretive explanation. That's where a system or a person is building some kind of account, an explanatory account of observed situations or events. For example, a geologist proposes a set of processes that created some landform, or a mechanic hypothesizes why a car doesn't start, or you're watching someone drive erratically and you make some inferences, like maybe he has a friend who's trying to get to the hospital. That's interpretive explanation. That is not about your own behavior. It's about things you observe in the world and you're trying to come up with an understanding of it. And then there's communicative explanation. That's where you already have an account of some events and you're trying to communicate it, convey it to another person or agent. For example, the geologist gives a talk at a conference about the model he developed, or the mechanic, when given you a quote for work to be done, actually has diagnostic notes on that. So the second, again, assumes that you already have something that is like what is produced by the first. And most importantly, the second doesn't really require the first. Turns out that the result of interpretive explanation can have the same form as something that you have generated yourself for your own behavior. For example, if a planning agent generates a plan to achieve some goals, then it's hard to think about that as interpretive explanation, and yet the result is very much like a plan you might infer by observing someone else's behavior. So communicative explanation applies not only to sharing existing accounts of external events, but also communicating about your own plans and activities and reasoning. And I'm going to claim that most of what we've been talking about in this workshop, and most of what goes on under the phrase explainable agency or explainable AI, is in fact communicative explanation, not interpretive explanation. If you go back to the older literature on explanation, like the 80s, it's mostly about interpretive explanation, like abductive inference. That's not mostly what we're talking about here, but it's good to be clear. And in fact, there are some connections. And the reason they're linked is because they can use the same kinds of representations. So whether an agent is constructing or communicating an explanation, it has to represent the content, the structural organization of that explanation. Now, in my view, explanations always refer to knowledge. You always explain X in terms of Y, where Y is something you already know. And I have a broad definition of knowledge. It could include the structure and the weights on a neural network, but it could also include a set of action models for a planning system. So you have that knowledge. It's usually generic knowledge, not concrete, specific stuff. And an explanation has a number of elements. There's a set of facts that can be given or things you observe. Optionally, there could be goals or queries. And then you have a set of instantiated knowledge elements. You take the knowledge that you had, pieces of it, you instantiate it for the particular situation at hand. For example, in planning, you would have a generic operator for, say, stacking a block. But now, in this explanation, you're stacking this particular block on this other block. So an explanation is a set of instantiated knowledge elements that link the observed facts, shows how they hook together. And there may also be annotations, for example, probabilities or an evaluation score for either some elements of the explanation or for the entire explanation. For example, you might have a overall quality of the explanation. The knowledge elements out of which you build the explanation can be logical formula, they can be causal chains, they can be numeric equations, they can be teleological relations. I did something in order to achieve this goal, but and they can even be pieces of a neural network. Okay, it doesn't matter whether they're handcrafted or learned. Okay, most explanations, non-trivial explanations, are generated automatically out of these elements. They're instantiated and then put together to build this explanation. Now, that's background, really. Let me come back to the topic of the workshop, which is explainable agency. And I mean, I think we agree that when a person makes a decision, that person can explain often the choices that he or she considered and why he or she selected one of them over others. And as far as I know, my colleagues and I coined the term explainable agency back for our AAAI 2017 paper. And I'm going to say an intelligent system exhibits explainable agency if it can provide, on request, the reasons for its activities. And that includes both mental activities, like a plan it generates, or its physical activities, so something that's actually carried out. examples, why did you prefer driving route A to work over route B? Well, because it had fewer traffic signals and it was still pretty short. Why did you swerve suddenly into the next lane? I did it to avoid hitting a fallen tree limb. Okay, so back to the earlier point, explainable agency in this sense is all about communicative explanation. Somehow you've already got a plan or a trace of your actions or even an interpretation of an image. Okay, that's happened, and now we're going to try and communicate it to someone else. In some sense, this is a metacognitive activity, right? You've laid down traces from regular performance processes like, say, plan generation or image understanding, and you're now going to operate over those traces. There's been some work on this. I wouldn't say there's vast amounts of work on explainable agency, starting with diagnostic systems back in the 80s, but also work on reactive execution. My colleagues and I did some work on personalized scheduling and route planning in the late 90s. More recently, there's been work on explainable planning and control. Most of these have emphasized one type of explanation, but not others. So I think I don't want to say that they're incomplete. They were helping us understand what the space is. I wanted to talk here about 3 types of explanatory content that are worth thinking about. The first is and this is probably the most obvious, is structural accounts. You might call them, sometimes they were sort of related to causal accounts. It's how the components of the explanation lead to the agent's goal. For example, you pick a route because you traversing each segment on the route will ultimately lead you to a destination. There might be other segments that if there was a segment in the route plan that didn't take you to the goal, that would not make any sense, right? So that would be not a very sensible explanation. So it's the logical or structural connections among the elements that help show how the agent led to a goal or gave it an answer. It could be for solving a physics problem, right? And you show how you can derive the answer from these things when you derive those from these things, and so on. This is closely related to Newell's definition of rationality. He said that an agent's action is rational if the agent believes that taking that action will help it achieve one of its goals. Okay? Rationality is not about optimality. Rationality is about doing something makes sense in the context of your goals. So those are structural accounts. And in fact, classic AI planning systems like partial order planners do that, right? They build a causal graph. So they have an explanation sitting there. They don't communicate it. They just show the picture. But that's what they're all about. But there's another kind. That's preference accounts. And that's why some solutions, whether it's a plan or whether it's an image interpretation, why some are more desirable than others. For example, one route is shorter than another, and it has fewer turns. That's why I preferred this route over this other route. And then the third type is what I call process accounts. That's about how you actually found the plan or the derivation or whatever it is. And since many of us adopt a heuristic search framework in solving complex problems, this makes sense that this is that the agent says I considered this partial route. I started to go down this path, but then I decided that, oh, there's a toll road there, so I'm not going to take that. I'll backtrack and find something else. So in planning the route, he started off doing this and then did something else. This is the kind of thing that psychologists would be most interested in because they're interested in the process of problem solving, at least some of us. There are other forms of communicative explanation. For example, why a candidate plan or solution is just not viable. For example, it violates some constraints. But I think these are 3 really important ones and are worth clarifying. And again, for the record, there's been a lot of work on the first. It's not called that. because it's sort of like, well, you got to have if you have a plan that takes you from an initial state to a goal, then it is in some sense an explanation for how to get there. There's also two modes for explanatory agency, two ways an agent can communicate. The first is reporting summaries of the structures it's created or its preferences to search. For example, presenting the turns and segments of a driving plan, like in a route map, or summarizing your actions in when carrying out a military mission. That sometimes these are called after action reports. Just generating those summaries is okay. I mean, there's questions about how much detail to give and so on, but I think a more challenging task is answering questions about these things. For example, which route did you consider? Which one did you select? Why did you select it? What plan did you execute? And during the execution, what happened when something unexpected happened? How did you adapt to it, and how did you replan? So the thing about question answering is it's very focused, and you have to look at particular elements of the explanation. It's not just giving a core dump. So to do explanatory question answering, the agent must, I would argue, again, remember, we've already assumed that the plan or the execution trace or the inference to why this is a cat in the image, that's already there, right? So, but we still have to be able to store and index these traces in something like an episodic memory, connecting the constituents so we can access them later. Okay, we want to be able to access them separately. Then, given the question, we have to turn the question into some kind of a queue that we can use to retrieve content from the episodic memory. And again, here we only want to access those parts of the stored structures that are relevant to the questions, right? So during this road trip you took, right? Why did you stop at this truck stop, right? I mean, there's nothing else about the trip you care about. I just want to know, why did you stop at that truck stop rather than of all the others that were along the highway? And so you have to store and index stuff. You have to then use the storage structure to retrieve just the pieces you need. And then, of course, you have to translate the retrieved elements in some understandable form. And if this sounds related to work on case-based reasoning, David, it's not a surprise. It's actually very similar in spirit, and I think raises many of the same issues. Now, these answers that you present to someone could be in language. It could be in graphics. It could be in some formal logical notation. I'm not taking a position on that. They're all valid. And it's pretty clear they should not give any more detail than necessary, because one of the Gricean postulates, you don't talk someone's ear off when they already know about something. So this is worth thinking about, and this is not the kind of thing you usually hear about when people talk about explainable agency or explainable AI. I think these are important. Now, we have heard talk about what I would call rationalizations. That's because of this issue of retrieval, okay? We know that people can produce reliable, think aloud protocols while they're solving a problem. That's how Newell and Simon came up with many of their early ideas in the late 50s. And they've done studies that show that people are pretty reliable about what they do. They can access their processes while they're happening. What they're not good at is retrospective reports, because they haven't stored everything or they've indexed it poorly. We don't quite know why, but they cannot access or retrieve all the details of their problem-solving processes after the fact. And then what that means, interestingly enough, is that retrospective reports, because they rely on what's called reconstructive memory, is actually closer to what I said earlier. It's interpretive explanation. It's like you're trying to generate an explanation of why in the world did you do something, and it turns into what we call a rationalization. That's all relevant to modeling human behavior. I think it's interesting. We don't need it for AI systems, though, unless you want to model the details of human memory retrieval. So I say, let's not do rationalizations. Let's do real explanations for why you really did things. Now, okay. That was about explainable agency. Now let me talk a bit about normative agency. Humans are goal-driven entities, but they're not, no man is an island, right? They have to operate within their society and its societies and these norms. I'm going to say that an intelligent system exhibits normative agency if, to the extent possible, and this is important, it follows the norms of its society. Examples: paying for food rather than stealing it, saluting a superior officer in the military, waiting in line rather than cutting ahead, recycling to help the environment. These are all norms of at least some societies or sub-societies. And these all direct or canalize people's behavior in certain directions, right? They sort of operate as guides or constraints on our behavior. And there are different types of social norms, right? There's formal laws, like obeying certain traffic signals, or military orders, like getting up at reveille. There's also informal customs. In Pittsburgh, when you come to a red light, if there's a car on the other side facing you that wants to turn left, when the light changes, you're supposed to let that first car go left, not the second, just the first. That's called the Pittsburgh left turn. It's a very strong custom in Pittsburgh. And if you don't follow it, you will get honked at, at least used to be. But there's also moral tenets, like life is more important than property. We don't state many of these norms explicitly. You don't learn them in class, right? But that doesn't make them any less important. And it does not mean we can't encode them as knowledge over which our agents can reason. And learn them if you want, but this talk's not about learning. This talk is about the use of knowledge for explaining your behavior, the use of knowledge to encode norms and how they hook together. There's also been work on normative agency, particularly in the areas of legal knowledge and moral tenets. But most of that work has focused on judgment, on evaluating other agents' behavior. Oh, would they do the right thing or not? Most of the stuff I've seen on moral decision making is about trolley problems, which I find tedious and not very interesting. But of course, there are any self-driving vehicle has, tries to follow the rules of the road and so on. But all that I've seen there is pretty shallow, and we can do much richer stuff. So before an agent can use social norms, we again have to represent them. And there's some issues here that come up. In the philosophy literature, there's a big distinction between deontological morals and consequentialist morals, as what actions to take versus what states are desirable. Another distinction is whether you should state norms in terms of qualitative relations or quantitative criteria like evaluation functions. And a third is whether you should focus on prescriptions, that is what you must do, proscriptions, which is what you must not do. The good news is these aren't mutually exclusive. In fact, I think you want all of them. And the architecture that I've been developing to try and encode do some of these things, that's the plan, is to have aspects of all of these in the unified framework. There are some challenges that I really think we need to look at. One of them is how do you deal with conflicting norms? For example, trading off legality versus safety, as an example, at the driving example I gave you, or authority versus morality, right? If your superior officer orders you to destroy a village, do you do that? And different people have different answers to that, unfortunately. There's a related issue is what's called mitigating factors that modulate norms. For example, in law, if someone attacks you and you defend yourself, that's considered, even if you kill them, that's not as that's more defensible than if you do it for no good reason. There's also issues about reasoning about others' mental states. For example, telling white lies. You do that as a kindness to someone, or following the golden rule. This is all about other people. And these tend to be very abstract, generic norms that are not very domain specific, but and are challenging in some ways. But once we've got these, once we have found ways to deal with these issues and these issues of representation and reasoning, then we should be able to incorporate social norms, these are knowledge elements, into existing methods for plan generation and plan execution. I don't think that's hard. I think it's mostly representational issues and figuring out how to encode to deal with things like these conflicting norms that involve trade-offs. Now, I've talked about explainable agency, and I've talked about normative agency. Of course, when we make a decision, we can often say not only what choices we considered, but how norms influenced our selection. And I'm going to say that an intelligent system exhibits justified agency if it follows society's norms to the extent possible and explains its activities in those terms. For example, I stole that food to help a starving child, right? I violated one norm in order to deal with another one. I disobeyed that order because it was illegal or unconstitutional. I confess that I have done this third one. I have occasionally cut in line to avoid missing a flight or breaking traffic laws for a medical emergency. Now notice all of these examples involve conflicting norms. And I'm going to claim that the most interesting examples of justified agency involve this. If it's just a single norm you're saying why you did something, it's not very hard. It's the trade-off issue that really makes things interesting. Now, to implement intelligent systems that exhibit justified agency, as I've defined earlier, then we're going to have to encode social norms. I think the way to do that is in terms of goals or motives, goal structures that generate goals, values or value functions, and constraints of some kind. So again, I think we can use existing languages, formalisms for doing that, but we still have to do it. We have to encode content about social norms for particular domains. We have to then have an architecture or a system that can use that knowledge to generate and execute plans that are guided by the norms. Again, we have to, as before, we have to store and index the products in something like an episodic memory. In response to questions, we have to retrieve the content that will answer those questions, and we have to communicate the results to the questioner. And if you do that, then whenever our explainable agent sort of clarifies why it did things, why did it pick that route, why did it take this action in the grocery store, it will have social norms embedded in the explanation. Some of the elements will be about achieving its own goals. Oh, I went to the store to get some meat, but other parts will be about, for example, standing in line, going to the end of the line. Why'd you go to the end of the line? Why don't you cut ahead, right? And the answer is, well, because there's a social norm. You don't do that, right? And so you will get justified agency as a result. Now, I don't know how I'm doing for time, but I'm almost there, David.
You're in good shape, Pat. You're in good shape.
Okay, then I'll slow down. No, I did that. I asked a speaker to do that once and it was bad news. So I've got, so this is all a framework with some, I think, plausible observations, but there's two hypotheses that suggest themselves to me that come out of this. One of them is that any intelligent system that supports both explainable agency and normative agency will just automatically exhibit justified agency. What am I saying here? I'm saying that that once you've got those two elements, those two abilities, you don't have to do any more work. Once you have stated social norms, a set of social norms in terms of goals, of value functions and constraints, and in way that your planner or execution system or whatever can operate over them, then you should get justified agency with no extra work. It should just fall out. I don't know if that's true. It seems plausible to me. But there could be interactions that we just don't foresee. Here's the other one. Remember, I distinguished between structural preference and process explanations. I predict that preference explanations will be the most important type when demonstrating justified agency. And that's because, as I said earlier, the most interesting cases involve conflicting norms and trade-offs among them, right? That's what, and when we justify behavior, if your behavior is questionable, first of all, we don't have to, you're not going to be asked to justify your behavior unless you did something questionable, unless you violated a social norm. And hopefully you will have violated a social norm because there was some other norm that was more important. So that's the prediction. No one's going to ask you to say what your chain of reasoning is, maybe occasionally. It's much less likely to say for them to ask you, unless they're a cognitive psychologist, to ask you to reproduce the search tree you explored to try and come up with this solution. It's really going to be about why'd you do this rather than this, and it'll have to do with something being more important than something else. Again, either of these hypotheses could be false. Both our notion of agency, our notion of norms could be more complex. Paul Bello at the Neal Research Lab has told me that he thinks I have an incredibly simplistic notion of agency. It's much richer than that. I don't know what he's talking about, but he's got a paper on it and in AI Magazine that's worth reading, and I'll let you explain it to me. Now, I have offered a theoretical framework for justified agency. It's a very abstract framework. I gave you some informal examples, but nothing very detailed. Obviously, we still have to develop architectures for explainable agents. For example, explainable planners. Encode knowledge about social norms, for example, for urban driving, which I think is much richer than people realize. Combine these components to produce justified agents, ones that exhibit justified agency, and demonstrate their behavior, for example, in driving simulators. Let's not do it on the road just yet, and evaluate them. And I'm going to argue that the AI community should be pursuing this agenda, both using different forms of knowledge, for example, action models and planning, causal models, neural networks. Pick your favorite representation of knowledge. Whether it's whether it's handcrafted knowledge or whether it's learned, that's not the issue. The research issue here is not about learning. The research issue here is how you use not only the knowledge you have, but also the internal structures, the explanatory structures you already have. How do you communicate them to others? And to do it on distinct problem types: plan generation, plan execution, even image understanding. We should be pursuing justified agency in all these forms. I'm not sure if social norms play an obvious role in image interpretation. That would be an interesting one to explore. Okay, so the main points: three layered ideas. Explainable agents convey reasons behind their actions. It could be mental actions, could be physical. Normative agents attempt to follow social norms. Justified agents explain their activities in terms of such norms. And then there's some challenges that arise for all of those, including how to put them together. And there were two conjectures. First, that merging the explainable agency and normative agency naturally gives justified agency sort of as a free side effect. and that justified agency is going to rely centrally on preference accounts, precisely because the interesting ones involve conflicting norms. Now, we need to test these hypotheses with controlled experiments in mission-oriented test beds. I think that urban driving is great, but David might want to do it with his underwater vehicles. There's plenty to do. So just to conclude then, designing and constructing justifiable agents is an important step toward reproducing the full range of human intelligence. I hope that's something that we all think is laudable. But the ultimate demonstrations of such artifacts would be self-driving cars that can convince judges in traffic court, police drones that defend themselves in civil suits, military robots that win court-martials for actions they carry out in combat. I want to encourage other AI researchers to pursue this vision. I think it's an audacious one of explainable, normative, and justified agency. Here are references to papers on this topic, and I'm going to put this slides up on my website, so you can access them later if you want. And I just have to mention this is a screenshot from a 1964 episode of The Outer Limits called I, Robot, which is based on a story written in 1939 by Ian O. Binder. I, Robot, that was the original use of it, not the Asimov collection. And in this episode, Adam Link, the robot, is accused of killing his creator. He did not, but there's a big trial, and he has to defend himself and justify his behavior. It's a great example of what I'm talking about, and maybe we'll get there someday. Although I hope that the robot's creators don't kick the bucket. Thank you.
Thanks, Pat. Great talk. Really appreciate your time and the effort that you put into this, and I see how you've tuned it for this audience.
Oh yeah, I should mention this is expanded version of a talk I gave at AAAI 2019 in the senior member track. David put me up to it, and I thank him for encouraging me, because it was bringing together two things I really cared about and figuring out how they might merge.
So I see two questions, and welcome the questioners to present them to Pat.
May I?
Hey.
Oh, Rosine, I think Grigori had a question first. Is that correct, Grigori?
Okay.
So I just would like to ask, first of all, thank you very much for the talk, because now it is clear what the explainable agency part of this workshop is about. And so to connect it to the machine learning part, I would like to ask that, is it possible that there is a system which is explainable or normative or justified, which realizes justified agency, and it has a component which is a neural network, which you can test that it's 95% correct, but basically you don't have any idea of how it works and why it works. I think this is actually a very serious problem with what the designers of self-driving cars are fighting.
Yep. So first, let me point out that it's not just neural nets. You could write a rule-based system that's so complicated that no one can understand it either. I've seen examples of that, and they're badly structured and so on. So any knowledge-based system, whether it's built by hand or whether it's learned, can be difficult to interpret. But again, we're not talking about interpreting the knowledge itself. We're talking about communicating a particular explanatory structure so we have a performance system that uses the knowledge, whether it's learned or built by hand, that uses the knowledge to create an explanatory structure. That could be a plan. It could be an interpretation of an image. And so as long as I'm not an expert in in neural networks or how you can explain the inference procedures. I do find heat maps to be fairly shallow, and I'm guessing that there could be other things you could do. And I know people here have been doing that, but the issue is not about whether the content is learned. Okay, the explanation is not about it. The explanation uses can use learned structures. The explainable agent can use learned structures to clarify how it reached its conclusion. So I don't know that I answered your question. Do you want to rephrase it?
Well, if you cannot trust the network upon which you base your explanation, then how can you trust the explanation?
Well, we're not talking about, well, okay. So again, this is not about learning, right? I could write a big expert system by hand and it could have errors in it, right? So you may not want to trust its conclusions either, but that's not the point. The point is that even if the knowledge base, the expertise has errors in it, the explanation itself is its reasoning chain, right? So whatever knowledge it has, you run it on a particular test case, it comes up with a plan or interpretation of image, and that may be right or wrong, right? It may be a bad plan. It may be a incorrect interpretation of the image. The explanation is still a valid explanation of how it reached that incorrect conclusion. And that's what we're talking about here, is how we can do that effectively. We're not talking about how you can get a learned neural network to do the right thing, but rather how can you get it to tell you why it did what it did, whether it was right or wrong. Is that not right or wrong?
Well, but then you are assuming that this neural network exhibits the behavior that you expect from it.
No. You just want it to tell you what it did and why, how it did it.
Well, yesterday it worked correctly, but how do you know that you can rely on it to work correctly tomorrow?
We're not talking about reliability of, say, a learned classifier. We're talking about understanding how a learned classifier or a handcrafted planner or whatever reaches its conclusions. We want it to communicate to us how it did that. Whether or not, and of course, once it's done that, that might help us see where it made errors. One of the reasons for doing this is I think we've had some talks here where the purpose of explanation is to help debug the knowledge base, right? So it can have this sort of higher level purpose. It's not just to understand it, it's to help get things on track. But the explanation process itself, and the explanation itself isn't right or wrong. It's a description of what the agent did. I mean, unless you're talking about systems that build rationalizations, which I don't recommend, which are just made up.
So next person who had a question was Rosina.
Yes.
Hi, Pat. Thank you. I'm a fan of this work. I really love it. My question is...
I just wish I had done more work in it. It's mostly right now I'm waving my hands vigorously.
So social norms do change. Have you seen any kind of work that could possibly be helpful to learn, so an agent could learn about changes in social norms? I mean, look at what happened this year, right?
Yeah, sure.
Wore masks before.
I don't, but most people, I agree. And so, yes, obviously they can be learned. I mean, they're a kind of knowledge. And one of the interesting things about social norms is I think they would be relatively easy to learn because they're social and we get feedback from others, right? I've certainly had people tell me that I should be wearing a mask in the store, and I tell them I have breathing problems and stuff. But I got that feedback, right? And if I wasn't quite so ornery, I would have learned to wear my mask. So I think it's a fairly standard learning issue. Now, whether you want to use deep neural nets or something else like some of the older ideas on explanation-based learning, which is a whole different role for explanations than what we've been talking about here. I think that I think that the role of explanations in learning is very promising, and we need to go back to that idea. But that's a separate issue I didn't want to talk about here.
Thank you.
Yeah.
Next, I think, is Shane.
Yeah, thanks. I just wanted to comment. You had said, I don't know if there's norms in image classification, but I think we see them in terms of simple things like Gricean maxims,
yep.
but also like the basic level, Rosh's basic level of categorization. This is a norm that the AI systems are terrible at. Like you look at a classifier and it doesn't know the concept of dog. It can tell you 40 different types of dogs, but it doesn't know dog.
I wouldn't consider basic level categories to be a social norm. I think the class standard argument for that is that there's something about the information that level of description provides that's useful for intelligent agents, and they would happen whether they were in a social setting or not. I was thinking more about whether there's certain things in an image, and some of them you just don't see because they would not be socially acceptable. I can imagine something like that.
Well, it's a social communication norm. It's a common ground norm. So it's not as the same type as.
So when it comes to communication, yeah, just to clarify, when I was talking about social norms, I was talking about them in the context of an agent's cognitive or physical behavior, not their role in the communicative explanation process itself. I see now you could do that, right? So you could, I did mention white lies. So if I'm trying to justify or explain my behavior to someone about why I took this particular route, I might not want to mention, well, I didn't want to drive past the house of my old girlfriend because I don't actually want, that would not be a topic of polite conversation. So I will just omit that. That would be an influence of social norms on the process of communicating your explanation to someone else. I wasn't even thinking about that until just now. Certainly that could happen. Wow.
So Pat, we have several other questions. I can't see them all in my chat channel. I believe I was just told that Harish has a question. Go ahead, Harish.
Oh, hi. So thanks for the talk. I'm still wrapping my head around a lot of the definitions, and this is great. I have a lot of homework to do now. Based on this grounding that that talk is giving. So my question is more definitional, sort of. So when you say a justified agency, and we're talking about all these norms, right? Can we encapsulate all of these norms in as the context, and can we say all these actions take context as a premise for an action that ensues?
I don't like the C word much more than I like the context, much more than I like the S word for salient. It's a hand wavy kind of thing that can mean almost anything. I would prefer to think about social norms in terms of David's done a lot of work on goal reasoning, right? Where do goals come from? Well, social norms are one of the ways in which you generate top level goals, right? You see someone who's not unconscious on the sidewalk, and suddenly you have a goal to go help that person. Or constraints, right? There's certain things shouldn't do things in certain contexts, like you don't talk in a loud voice in the library. So is that context? Sure, it's a way of encoding context, but I would prefer to talk in terms of sort of standard AI psychological terms like goals and constraints. I think that's more useful.
Thank you. Yeah, the reason I was saying context was the way I think of context is a norm that is localized in space and time, like Rosina was saying. Okay, 2 years ago masks were not the norm, but you know the social norm today is.
Sure. No, it's just that I think there are plenty of kinds of contexts that aren't about social norms. That's my issue. Is that yes, social context is real. Social norms occur in a social context, right? I mean, many of these norms have conditions, right? So like you don't speak, you can talk loud if you're out in the park, but you can't talk loudly when you're in the library. So there's a condition on the behavior, or you must do certain things under certain conditions. So the conditions are the context. The norm is the conditions and the thing you're supposed to do or not do, or how important it is under those conditions.
Thank you.
So I think Marquine stepped out, but correct me if I'm wrong, Mark. Tobias, you brought up a couple of issues earlier. You want to bring them up to Pat?
Yeah, I would love to. Even though you actually answered my question already, I think, the first one, but now I have a follow-up question.
Okay.
And my first question was, you had this branch example on the road, and if I avoid it, then I had a reason, and you had this as an example for explainable agency. And I was wondering if this is an instinctive reaction or an instinctive reaction, then I probably did not have reasons for this. So is this the explainable agency?
So, you know, I see Mark had a similar kind of comment too. I didn't want to go, you know, take an extreme position on what we have access to. Even when we're doing think aloud protocols, I don't think we have direct access to all of our reasons and so on. We can give a lot of information about. We're not nearly as good at telling you later why we did things. But okay. Think about an AI planner. Okay, it carries out search through a space of plans. At each point, it's considering what actions it might take, and so it's aware that it's got these 5 different actions it could do. All of their conditions are satisfied, so it could do any of them, and it has to decide which one to do. And now it's got some criteria for selecting among them, and so the lower level of calculating that whatever heuristics or evaluation function you use to decide which one to do, that may or may not be inspectable. There's plenty of evidence that people don't do decision theoretic analyses for making decisions, even for things like buying houses. That they use simple heuristic methods that are very easy, are not cognitively taxing, and so yeah, I think a lot of that lower level stuff happens very quickly, effectively at an unconscious level. Not always. Sometimes it's pulled up, but often it's unconscious. And of course, if you're not aware of it when it's happening, you're not going to store it and be able to retrieve it. That doesn't mean we can't have AI systems be conscious of it and have them store it. There's no reason why we couldn't store the scores of each possible action. And later on, we come back to it and say, well, why did you pick this over this? We go, well, look at the scores. And you don't have to give all the scores. You don't have to do the full calculation. You can say, well, this particular attribute was dominant. That was the one that was most important, and it vastly was much higher than this other alternative on that dimension. So that's why I picked it. There's different ways you could do it, but again, of course, no matter what you do, there's going to be a level below which you cannot go, and so I don't mean to say that explainable agents must be able to go down to the quantum level in order to tell you what's going on, but there will be some levels, and how you deal with those is interesting.
Okay.
Tobias, did you have a second question?
Maybe a little bit of a follow-up question, yes. I'm asking because I really liked some keynote by Hector Geffner, who compared like planning system to analytical minds and neural networks to more like intuitive minds and intuitive thinking.
Yes,
okay.
I'm aware of this, and yes, of course, you can do that, but there are, there are reactive controllers. If you look at human cognition, okay, we start off in any particular domain as a novice. We don't know much about it, and then as we gain experience in the domain, gain expertise, we can do things more rapidly with less explicit thinking. It becomes almost a knee-jerk reaction, right? So it's not an accident that it's chess masters who can play lightning chess. It's because they have such compiled knowledge. And in fact, if you ask them why they made that move in lightning chess, they won't be able to tell you because they just did it, right? But if you ask a novice, they'll be much better at telling you why, because they went through this long, drawn-out process of figuring out what the right thing to do is. They're so slow because they're going through. They don't have the chunks. They don't have the patterns stored in memory. So, as we gain expertise in any domain, whether it's automobile diagnosis or physics problem solving or chess playing or driving, we become more efficient, and we lose access to the lower levels. And that's how we build up higher and higher level skills. To say that one of those is planning and the other's neural nets is just wrong. I mean, I think not useful. You can use neural networks as part of the evaluation process in planning, as we saw with some of the fancy game playing systems, right? It's not one or the other. It is a distinction between a conscious deliberative processing and more automated routinized processing. I would use the terms system 2 and system 1, except that I think that gets a lot too much airplay. Psychologists have known about those two levels for 50, 60 years. That wasn't a surprise. Kahneman just coined a nice terms for them. So yeah, I'm not saying that there isn't a conscious planning and unconscious recognition. That happens. It's not symbolic versus neural, though. That's a nonsensical distinction. If you look at a neural network, you could use a neural network. You could look at the steps of a neural network, and there are versions of neural networks that are effectively doing more conscious like processing.
Sylvia, I think you had a question. Is that correct?
Are we really have time, David? I'm happy to go on all day.
Well, here's the situation, Pat. You caught us at a time. I don't know how this managed to work out, which we managed to have a gap in the schedule such that the next activity doesn't start until 25 minutes past the hour. That's
okay.
Currently 34 minutes from now. So while I'm sure some people would like to have a break, your talk's interesting and there are lots of questions. So
okay, carry on.
Sylvia, did you have a question?
Yes, but it's a bit okay. So my question is related to the fact, also to the things that you were telling before, like if an agent explain why it took a path instead of another. Can you? I think I lost connection. Can you hear me?
Yes.
Okay. So if an agent explain why you took a path instead of another, or explain the reasoning behind certain decision, why this could not be used for optimizing the knowledge of other agents interacting in the same environment?
Sure, I could.
And I'm thinking more also like reinforcement learning multi-agent setting, but I'm not excluding human agent settings. So also like the possibility to learn from the explanation, from the explainable.
I'm still not sure why people are so excited about reinforcement learning, particularly model-free reinforcement learning. I mean, learning evaluation functions to guide search is a great idea. And if you view reinforced learning like that, then certainly, if you did that, then what? So but let me come back to the point. It doesn't matter whether the knowledge, the expertise used in the explanation, used in the planning process or the control process or the image understanding process. It doesn't matter whether that's learned or not. Okay, you got it. Okay, and now if you're saying, well, can I, in the process of explaining why I did something, can I use that to teach someone else how to do it? Yeah, I think that could happen. Certainly, arguably, some of the best teachers are ones who can. I mean, it's all about them. They have procedures or knowledge in their head, and they want to convey it to someone else, and they do it often in the context of particular examples. Right? Here is a physics problem. Here is how I would go about solving it.
Yeah.
And I'll go through the steps, and so certainly that can happen, but explanation is a key role in education, certainly in good education. Explaining why. In fact, there's some really interesting work that Randy Jones and Kurt Van Lane did in the mid 90s on what they called self-explanation. They were modeling results they found with students who were solving physics problems. Turned out that you're given a worked out example, and you're given some general abstract principles for how to solve these things, and then turns out that some students will learn how to do that particular procedure, but there are things that are not mentioned explicitly, and so some students just learn it by rote, and some of them try to fill in the gaps. And they end up learning new knowledge structures, new rules that help them complete an explanation, and they get much better generalization to new problems. It's called the self-explanation effect. And now you can imagine building a tutoring system that tries to encourage that kind of thing, and it's certainly related to explainable agency. I think it is. Now that you mention it, I haven't done any work in tutoring systems, but systems that explain what's going on rather than just teaching what the steps are, actually trying to explain things, I think would be very valuable.
Yeah, not just curriculum learning, but explaining how real explainable agency, in the sense that they explain how they reason upon certain things. So, sure. And why they did a certain action. And
I've certainly had many people instruct me on social norms over the years, and David's laughing because he can remember particular examples. It turns out I'm an extrovert who, when I was younger, I lacked social skills, and you can just imagine that's a recipe for disaster. I was always trying to interact with people and doing it badly, and so I had lots and lots of negative training cases.
But this would work also if you have not a fully knowledgeable teacher. I mean, even if the agent who is explaining is not fully knowledgeable about the task, just trying to explain certain.
Yeah. No, I mean, certainly every time I give a talk, I learn something new because I'm trying to explain these ideas to people, and then I get a richer and deeper understanding myself. So yes,
this is what our systems need, Pat. Right? Sorry, went meta there. Excuse me.
It's okay. Yes, I think. I mean, I didn't mean to suggest that this is all there is, right? Certainly, lots and lots of things to do. In fact, one of the things I just finished an essay on explanation for the journal I edit, Advances in Cognitive Systems, and it talks about this distinction between interpretive explanation, classic sort of abductive explanation of medical diagnosis or plan understanding, and communicative explanation, which is, again, I think mostly what we're talking about in explainable agency. And at the end, I talk about well, where do we go from here? What else is there to do? One of the things is you could have an agent that does plan understanding or interprets an image, comes up with an abductive explanation for what's going on there. That's not talking about its own behavior. It then communicates that explanation, that interpretive explanation. It communicates it to another agent, and then that agent must then pass its understanding of that on to a third agent, right? So the middle agent's the AI system, right? So a human says, well, here's what's going on here's what I think why this person's driving so erratically. And then the AI system has to understand the explanation and then maybe fill in some gaps, add some detail, and then pass it on and explain it to another human. That would combine both interpretive explanation and communicative explanation in an interesting way. I don't think we're close to doing that yet. It sounds a little bit like what you're talking about.
Yes, I think I could continue asking if someone doesn't stop me.
Well, hold on to one, Sylvia. Are there any other people who have questions for Pat right now? If so, please unmute and ask them right now.
So I guess I'll chime in, and then this is more not to belabor the point of social norms, and I can only comment as a citizen living in society, not as an expert on social norms per se. But I do find it interesting, Pat, that you mentioned that you steered clear of psychology because of the difficulty, because I find grappling with social norms equally as challenging, especially the current state of society that we're in. But I would really like to know what thought you've put into on two facets around social norms. One, how you would converge on what qualifies as a social norm, and two, just the evolution. We've kind of touched on that a bit with the mask wearing and so on, but I mean, I could just enumerate a number here in the US, around, gender, race, identity, so on, that is just super, super fluid. So that's why I just see it as a very big challenge. So again, your thoughts on the convergence?
Okay. Again, I could have talked about moral agency. I didn't, right? I talked about normative agency because I was trying to be more inclusive. We certainly want agents that follow the laws, unless there's a good reason not to. We want agents that follow customs, unless there's a reason not to. And so I explicitly listed different types of social norms because they're sort of recognized categories. Do I want to enumerate them? No, but I think that that'd be a great exercise. This is the kind of thing that you've got students in a class, have them write down all the laws, the driving laws that they can think of for driving in a city. Write down all the informal things like, stay within a certain distance from the person ahead of you, right? Or don't change lanes too quickly, right? There's probably aren't laws like that, but they're probably not good ideas. Have someone list these things. Then once you've got them, there's a separate issue about how you encode them. You want to do it with logical rules, fine. If you want to do it with neural net, that's fine. You want to do it by hand or learn it, that's fine too. Although if you're going to learn it, you got to get a source of training data. So I don't want to be constraining, although there are obvious examples that come to mind if you're thinking about driving, because many of us drive, and we've got, if you don't think your behavior is constrained by social norms for your driving, you're just not thinking it through, because there's just all over the place. And I mean, I'll tell you, even I don't know if anyone has driven with me as a passenger, but I am a backseat driver, and if you probably more with my partner than with someone I don't know very well, because I'll tell you my opinions more readily, but that's a great way to discover differences in social norms, is to get in a setting like that where they'll sort of elicit differences. Why did you not turn at that light? why did you let that person cut us off? Why didn't you honk at them? That was rude. Sorry. I'm reliving experiences now. So I don't know. But do norms change? Sure. Have we been through a very strange experiences in the past 4 or 5 years? Yeah, we have, but probably no worse than in the 60s when other weird things were going on then, or even the late 1800s. My understanding is that there were radical upheaval back then. So it happens, and we adapt. And can we build AI systems that adapt? Sure. Again, my biggest, although I did not talk about machine learning here, I still am interested in machine learning, but I'm interested in the kind of learning that people do, which is much more rapid than most neural nets exhibit. And we have plenty of examples of learning methods that I believe could learn social norms very rapidly. Matthias Schutz, who's a professor at Tufts who works on human-robot interaction, he has done some work on very rapid learning from single training cases, and he's also done some work on social norms. I don't think he's combined them, but he may. He and Bertram Mall, is he on a panel later today?
Yes, he is.
Yeah, maybe let's ask him. They've collaborated.
Pat, can I ask you to relinquish your controls of your screen, please, so that I can see the other people in the session? Again, we welcome any more questions. There's certainly more time for anyone to ask.
And yeah, thanks for the elaboration, Pat.
Sure. And masks don't help.
Okay, going once. Any other questions?
I would like to ask a follow-up question about the type 1, type 2 reasoning stuff. Like going away from the neural networks, but just if I have a system like those reinforcement learning systems for chess, for example, where I use one part of the system, in this case it is a neural network, but it doesn't matter,
right.
For this intuitive part, and I use another part for the planning part, would you restrict yourself to explaining the planning part, or should we also look at the intuitive part?
No, I think that yeah. So let's go back to the 1960s or even late 50s and some of the early game playing programs like chess playing programs. They were clearly doing search through a space of trajectories, to play the game, considering if I do this, then they'll do this and so on. But they also had numeric evaluation functions. Now, clearly those are different, but the evaluation function is supporting helps guide the search. It's playing the role of a heuristic. That's not the only kind of heuristic, right? You can have rules that say don't do this under these conditions, or you should do this or prefer this. It can be symbolic knowledge too that plays the same role. And there are AI systems like SOAR and Prodigy that have search control knowledge stated as rules, but it's more typically done as some kind of numeric evaluation functions. And if that's encoded as a neural net, that's fine. If it's a simple like linear evaluation function, there's no reason not to store that. And if someone wants to know, well, why did you pick make this choice rather than this choice, you could certainly do that. I think a more interesting question is not whether you are explaining both the lower level numeric calculations, the evaluation process, or the higher level of steps. A deeper question is, well, deeper, I don't know. I think a more useful question is, do we want our systems to explain their step-by-step activities, or do we want them to explain more global things? Okay, so I'll tell you a story. When I worked for Mercedes, for Daimler-Benz back in the late 90s, we started a project on learning route preferences. It was going to be a personalized in-car navigation system. you would type in a destination, it would give you back, it would help you figure out what route to follow. Now, I had done some work on learning search control knowledge, and I said, oh, well, we'll track where people drive, and we'll see when they turn left, when they turn right, and so forth and so on. And we'll use that to learn control knowledge about, and that'll tell us what routes to propose. And we decided after about 3 months, that was nonsense, that wasn't going to work. Instead, we used an off-the-shelf route planner to, we used an off-the-shelf route planner that required an evaluation function, a linear evaluation function to guide search. It would find a route using that, and then we would show that to someone, and they could modify that. Say, well, I want a route that has fewer left turns, or a route that has that's faster, and it would then modify the weights and generate another route based on that. And based on, eventually they would pick a route, and then we would change the weights so that their personal profile was a set of weights on route features. The explanation would have been, well, I like this route better than this route because if this driving time times this weight plus this number of turns times this weight, so it's better than this other one. But it was the explanation was at the, we didn't talk about it as in terms of explanation, but clearly we could have done that, was at the level of the entire route or the entire plan. We did the same thing with scheduling, right? So this is where I came up with a distinction between process accounts, which is how you found the solution, and preference accounts, which is the quality of the solutions. And I think that unless you're a psychologist studying the nature of human problem solving, or unless you're a programmer who's trying to understand why a system is finding a crummy solution, we're mostly going to be interested in preference explanations. That's my take. Especially when social norms get involved and where there are conflicting norms.
Okay, thank you very much.
Yeah, thank you. Any final questions? We could go on for a few more minutes. I figure we'll give ourselves a 10-minute break before the 25-minute after the hour session starts. Any more? Okay, well, thanks, Pat. Really greatly appreciate all your time in answering all these questions.
It was fun.
Yeah, it's fun listening to it as well. So thanks so much. Appreciate this.
I always enjoy listening to myself. Yep.
As well, as Harish was saying earlier, there's a lot to ingest here.
Okay.
So,
thanks again, and I'll see you after. We do have when do we come back again?
We have a break that lasts until 25 minutes after the hour. We then have 4 presentations, then a short break, and then the panel.
Okay, thanks.
All right, thank you very much. Okay, folks, we'll come back at 25 minutes after the hour. Thank you.
Thank you.
Okay. So then welcome to my talk. I'm Jakob Michael Schirmer. I'm a PhD student from University of Hildesheim in Germany. And my topic is explainable case-based reasoning. And the motivation behind it was that I was looking to find ways on how case-based reasoning is solving problems in terms of explainability. So I wanted to figure out what approaches have been used, what approaches have been tried. And as you heard during the last days, during the AAAI, there were a lot of different approaches in terms of explainability. And the question is, can case-based reasoning be one of them? And currently there is seemingly nothing like this in the CBR community to find. So I wanted to create a place where somebody or any of you, for example, any XAI researcher or any CBR researcher can go to and can take a look at. So problem solving in general is basically the question how humans solve new problems. So some of us try to apply logical rules, logical thinking, but if that's not applicable, then we try to consider the context of a given problem, especially in situations, for example, if you have relationship problems or anything like that, where you cannot always follow logical rules, but need to see the bigger picture or the context of the person. And some of us might search in our memories for similar situations. For example, your car broke down and you, in the past, you had a similar car. And then you're trying to figure out what was the situation back then? How did I solve this situation? And can I apply the old solution to my new problem? So this is basically what case-based reasoning can model. So for those of you who never heard of case-based reasoning, it's basically consists of out of 4 steps: retrieve, reuse, revise, and retain. And additionally, it uses knowledge containers, which I will come in a second to. But initially you give your problem, which is basically described by a situation, which has attributes with certain values, or values that are undefined because you cannot measure them, or they are just unknown. And then you're trying in the retrieval step to find the most similar case. So you're looking for the n best matching cases, like with k nearest neighbor or any similar approach where you can find similar cases. Then you try to apply this situation or provide this similar case or the most, for example, 5 similar cases to the user. And you can also try to use adaptation knowledge. So you can still try to adjust the best solution and adapt it with adaptation knowledge, which is just one of the knowledge containers, and try to improve your situation. Then on the revise step, you may incorporate feedback obtained from training or obtained from user feedback. And on the retain step, you may decide to save the case, so your current problem with the solution that has been applied to. Or you can also think, if I always save every case that I encounter, then the case base may grow too large, and then we can run into maintenance problems. So we can also decide to just adjust similarity measures. So knowledge containers support the CBR cycle. So while we are trying to retrieve similar cases, we, for example, use similarity measures. We use local and global similarities. We use vocabulary. I already mentioned adaptation rules. And of course, we have a case base that we are getting our cases from. So we are storing basically our knowledge there. And the important step is, or the important point is, that those containers may contain domain knowledge and reflect also context, since cases are already always situations that actually occurred, but they don't necessarily need to contain domain knowledge. They can also be more, for example, objective. And this was also a point before my research where I was thinking that could be some kind of interesting if more CBR approaches are rather using domain or model-based approaches or model-agnostic approaches. So in general, for the research or for the question, what do I try to approach, or why using case-based reasoning for explanations? Well, first of all, to define explainable case-based reasoning is basically using CBR as a methodology to provide explanations. And CBR is often praised as transparent and realistic model, since, as I wanted to motivate before, it's basically problem solves the way that we, or some of us, are problem solving anyway. So it might be intuitive to say that that in a similar approach of problem solving, that it may become more trustworthy. And additionally, supervised case-based learning can already obtain reasonable results, excluding sensor processing tasks where we don't really have the evidence for, if I'm not mistaken. But in general, the research question was, can CBR be used to provide helpful and especially personalized explanations? So what we did for the research was looking for keywords like case-based explanations, explainable case-based reasoning, XCBR, explanation patterns, all those buzzwords basically that you can find in the literature, and also substituted explainable with interpretable and transparent, and also included goals of explanations such as justification, transparency, to get a bigger picture on that. Additionally, when I found something relevant in the paper, then I also added up an author-based search like with Google Scholar, ResearchGate, or the DBLP University TRIA library, and to look at did the authors did some similar research in those areas so that I could find more results basically. In numbers, the results, we reviewed 261 documents, and out of them, 52 has been deemed as relevant based on explanations of their CBR system, CBR approach, rather if it was an implementation or just in theory. And of course, not surprising, most of those relevant publications on XCBR have been found on conferences like the ICCBR, which is basically the conference for case-based reasoning, but also additionally on workshops during the ICHCAI since 2017. Some workshops on XAI, of course, and some of you may have encountered CBR there. And based on these results, or based on these contributions that we found, we wanted to try to build a taxonomy that depicts and categorizes the most frequently occurring themes. And we might discuss, or you can discuss and argue later if this was successful or not. But basically the goal was that you can look at the taxonomy and figure out what the CBR community has been done in terms of explanations. So for example, if you say I'm a person that is basically working with graphs, and then you can distinguish between using graphs on model agnostic or model based approaches, then you can go down the taxonomy and find some approaches there. So what I wanted to motivate before, when I was thinking about rather more model-based or model-agnostic approaches used in CBR, I found way more model-based approaches, which is kind of also not surprising, but also some model-agnostic approaches, and this is the most discriminant factor in my opinion. So that was the first approach where I thought this was a needed distinguishing there. And the branches to the most left and to the most right side, like definition and visualization, of course they are needed. Of course, people talk about them. If you are talking about explanations, then of course you have to define it. You have to find suitable visualizations, but they also influence model agnostic and model-based approaches. So of course, model-based approaches also use visualization for explanations, etc. So those areas kind of intertwine, but still I want to sort them out, that if you're looking explicitly for what kinds of definitions are the CBR community using in terms of explainability, you can go here. So this is basically how it branches out, and I'll go here through kind of faster, because this is always just an example. So for example, in terms of justification, Olsen and his colleagues were talking a lot of how to answer the why questions. Transparency has been discovered, or not discovered, but discussed by Lillehaug, etc. But also, of course, other authors also discussed about this. So these are just examples. And if you're looking for more references, more examples, then those are in the taxonomy, or rather in the paper, of course. So for definitions in XCBR, it's not surprising that they mix up quite well with how definitions, how goals, and how kinds of explanations are also defined in the XI community in general. So I think there's nothing really surprising here. But what I wanted to show you with, in terms, for example, with model agnostic approaches, like searching for the nearest neighbor, which is very important for the retrieval step. There are some probabilistic approaches, for example, by Olsen et al., by using machine learning methods to define a similarity measure to predict the error of retrieving incorrect cases, because as you can guess, CBR lives and dies with similarity measures and retrieving correct cases. And so here the approach is to find a way to gather correct cases by using machine learning approaches. And this is really superficial here described. If you want, we can go more into detail in this discussion or in the paper, but I want to give a broader overview here. So in the next example, counterfactuals have been discussed by Keen and Smith, and here also CBR is combined with neural networks to find the nearest unlike neighbor, for example. So this aligns up with the discussion that we had just in the talk before, and also in the keynote from Tim Miller, where the question was, why not this and this and this? So this has also been covered here. And also the leading by examples like the with recommendation systems. So recommending movies based on the attributes users like is also covered here by Joe Aragoneses. In terms of graphs, so if you are more into graph structures, there was work from Victor Eisenstadt and his colleagues in, for example, transferring a floor plan into graphs and then combining those graphs or comparing graphs to each other, and then prepare these as a query to the user with the similarity. So also as an explanation. For workflows, you can compare event traces, you can display parts, which part of workflow contributed to the similarity calculation. So the core sense is that similarity description or the explanation of the similarity is always a bigger part of the explanations. And routing follows the same rules as workflows, basically. For the model-based approaches, I wanted to motivate that XCBR is in this kind of sense nothing new. So CBR back in the days has also been modeled or designed with explainability already in mind. So for example, Agner Amott and his colleagues employed a CBR system called Creek, which used knowledge, general knowledge combined with models. So very model-based approach to find similar cases. And this approach has also been adapted later by his colleagues with Bayesian networks, which we also heard this morning, or depending on your time zone, which can also be used with CBR, basically. And ontologies, we also heard in Pat's talk, he also referenced Ashley. So in the legal domain or in legal reasoning, there's also which is a very structured domain, and where you can also see people are judging based on what happened before. This is also a very good opportunity to use case-based reasoning as explanation, because that case happened before. This is your judgment, basically. And another very interesting paper in terms of classification has been, would recommend Ford, Kenny, and Keen with ANN CBR twin system, which is asking the user if the classification that the system has done was correct. A quick note about visualization, and also here going back even to Roger Schenk with 1986 with explanation patterns, which also have been revisited in the last years. So these are the most important basic foundations, which is basically free text with which you can fill in with your attributes and values, and these can also be used as an explanation. Then we have also very much research in free text explanations, mostly using justifications or counterfactuals. And we had also 2003, 2005, a system by McSherry, which was also more a discussion system. And his approach justified recommendations on missing attributes, also based on users' preferences. So what I wanted explicitly to show you as what I think is a really nice example of a case-based visualization is the approach of Jean-Baptiste Lamy in 2019. So here you have a system where you have for one part on the left side the scatter plots and on the right side the rainbow boxes. And in the middle you have your query. So this query number 13 is your case. And this system is a system which tries to identify rather if the breast cancer is benign or is it malignant. And you can see here as that the system per se doesn't really build an explanation, but it shows how the similarity has been assessed. So
Jacob, 3 minutes.
Yep, thank you. So you see here 3 attributes, or a lot of attributes, where you can see bare nuclei greater than 3 goes to malignant. And the heat of the box describes that this attribute is very important to the system. And the width of the topper box here on case 15 describes that this case has been deemed very similar. And if the attribute occurs in both malignant and benign classification, then it becomes orange because of the mixture of red and yellow. So the explanation is basically saying, or asking the question, what is the dominant color? And then you can see why this color or why this classification has been chosen. So just to conclude, the lack of course, also in CBR, we have a lack of user studies. So we still also need to experiment with our approaches and need to figure out if the user are satisfied with our approaches. Machine learning approaches, we heard, are becoming also very good, and they are less suffering from black box problems. But also, as I mentioned, we can really combine case-based reasoning with machine learning, for example, and also retrieve better results. And for future work, we still need to figure out the importance of the receiver of the explanation. So individuality, personalization, etc. And also what kind of explanation is for the average user. So if I don't have a guess about the user, what is my best shot, basically? So this is the very quick overview, and I'm happy for the opportunity to talk here, and I'm open for questions.
Thank you, Jacob, for that great talk. Is there any questions? Are there any questions? I have a small question if no one else has a question, but this may not be strictly related to case-based reasoning, but I saw in the slide, I saw an explanation type of cognitive explanations. After in the app. So can you maybe explain a bit about that?
Cognitive explanations were mostly, if I recall correctly, with also more about visualization, basically. So how, for example, on which parts of an explanation somebody is really focusing, or which part of an explanation is what actually gets to the explainee. So for example, you can have a big text of explanation, and what actually is the people who got the explanation, what is he actually understanding out of that?
Right. I think that's all the time we have now. Maybe we, if there are any other questions, you can ask in the Robert chat. But yeah, thank you, Jacob, again for the wonderful talk.
To stop share, right?
Yes. I think the next speaker is Adam.
Yes.
Adam Jones.
Correct.
Jacob is still okay.
Okay, great. Thank you. Okay. Can everyone see my screen?
Yes, perfect.
Yes.
Over to you, Adam.
Okay, thank you, Prashant. So I am Adam Jose, and I actually had the privilege of completing a bit of work with Denise Augusto and Rosina Weber on looking at the qualitative investigation that is being performed in the XAI research. So we are all from Drexel University's College of Computing and Informatics. So what I want to do today is I'm hoping that after I speak, that you will be left with 2 primary takeaways. So the first of which is going to be a different lens with which you view qualitative data through, and the second are a set of recommendations. So given that I want to leave you with these takeaways, I would also like to lead with these takeaways. So specifically in the context of the collection and analysis of qualitative data. Anytime you use interviews as a method to collect qualitative data, it's important to specify the format of the interview and to also provide an overview of the interview guides that you used. We've seen in the literature, many individuals have used coding methods that are part of the grounded theory coding canon as part of their analysis, but it's important to ensure not to claim utilization of the grounded theory methodology if you're just using the coding methods part of grounded theory. Something else that we also found, and this draws from the work, from the DARPA XAI team and what Shane has, already spoken to, but interviewing is actually a method that can potentially be valuable for studying mental models in XAI and also potentially the trusting process. So we just want to put that forward to the community for consideration. And I'd say probably the core underlying thread and the message that we would like to leave everyone with is to please consider collaborating with experts from social disciplines toward bolstering rigor and effectiveness in user studies. So I know that you're probably thinking, okay, how did we come to these recommendations and what exactly motivated us to look into this? So one thing that we've noticed for many of the papers that we have read in XAI research is there has been many instances where qualitative data has been collected from human participants, and a lot of the insight in that data has actually been untapped. So naturally, we've also been motivated by, Tim's work, and again, the work out of the DARPA XAI program of being able to really incorporate insights from social science corpora toward helping advance XAI research. But that's something that we've seen. So we wanted to actually conduct a focused analysis of papers that have been published conducting XAI research to really spotlight those opportunities for enriching user studies. So our motivation actually does align with some relatively recent work where there have been other calls from the community that have really tried to push or just really advocate for interdisciplinary collaboration, and again, toward the benefit of user studies in XAI. So with all of that motivation in mind, what we'd want to do is actually just draw attention to some of the qualitative research literature, really with the aim of catalyzing more systematic qualitative investigation as part of XAI research. So it is important to really situate the discussion. So there will be a little bit of terminology that we do have to discuss at the beginning. But again, it's important just to situate our perspective so everyone understands what I mean when I'm referring to qualitative data. So there are actually many instances in the AI literature where qualitative has been used to properly describe analyses that extend beyond just the maybe traditional quantitative analysis. But in the qualitative research literature, qualitative actually refers to a naturalistic orientation to the world, namely the meaning that research participants actually bring to any phenomena under investigation. So anytime that qualitative is being used in this presentation, in the paper, and as it refers to the collection of qualitative data from human beings, it's really to study those human facets of a topic. So to very crudely distinguish between quantitative data and qualitative data, the former is typically numerical, whereas the latter is typically non-numerical. And mind you, this is not an attempt to establish a false value dichotomy, so to speak, between the two different types of data. There are many, many researchers who conduct mixed method studies and embrace the complementarity between quantitative data and qualitative data. Mind you, this is just a very, very crude distinction. So we're situated in this discussion to really understand what I mean when I'm referring to qualitative data. So in the analysis of qualitative data, there may be a term that some of you are familiar with, and this is actually reverting back to one of the recommendations that I opened with, coding. So when I mentioned how crucial it is to not claim utilization of the grounded theory methodology when individuals just use grounded theory coding methods. So what I mean is a fundamental data analysis technique that's used to analyze qualitative data toward identifying patterns or even supporting categorization. But in this context, it's important to not conflate code with coding that we discuss in computer programming or in semiotics. So I believe this was from the last HCAI XAI workshop, but Komick and Schuster actually nicely communicated that XAI studies can adopt either a quantitative, qualitative, or mixed methods design. So why is that relevant? Well, part of the challenge in this work was really figuring out how we can, one, properly delimit our scope to where we can, two, really present a coherent analysis to the community. So what we wanted to do was really limit the analysis that we conducted to XAI papers where some degree of qualitative design was adopted by the authors as part of user studies. So that can be strictly qualitative designs, but many were going to be more so mixed methods or even within experimental designs. And because there are myriad methods that can be used to collect qualitative data, we also had to be thoughtful of how we could frame and analyze the papers according to the methods that are out there. So what we wanted to do is we actually looked to the literature and we just said, okay, we'll just focus on the 3 most common methods that has been established in the qualitative literature that's commonly used for investigation. And those happen to be interviews, observations, and focus groups. So just very briefly, observations are actually a method that researchers can use to inform an understanding of research context. That can include participant behaviors or data on processes. Interviews are actually used to capture insights directly from participants. Now, there are 3 formats of interviews. So structured, semi-structured, or unstructured. Remember when I mentioned in the recommendations, how crucial it is to make sure that we specify the format of interviews that are used. And when I say that, I mean one of these 3 formats. So either structured, semi-structured, or unstructured. The 3rd most common method, focus groups, that's actually a form of interviewing as well. It's referred to as group interviewing. And it's actually very useful to elicit data from participants that would have otherwise been undiscoverable simply by taking advantage of what transpires as a result of group dynamics. So definitely different applicability and utility from the different methods. But there's actually a 4th method that is quite germane to XAI, and the DARPA team has been very helpful in putting out information and publishing on this aspect, but questionnaires, or just surveys. Now, when many of us may think of questionnaires, and we may think of the questionnaires that actually collect quantitative data that has to be statistically analyzed. But what we may not think of is anytime open-ended questions are included in a questionnaire and a respondent provides a response that actually yields qualitative data, and that has to be coded as part of analysis. So as I mentioned, you can also collect qualitative data as part of experimental designs. And when that happens, that's often toward understanding how a human experienced some sort of experimental variable, whether that's an intervention or so on. And that's a form of mixed method study design. So why it's important to understand that is, again, just coming from a sense of terminology and how we can make sure to articulate our findings, we decided to refer to any questionnaires that were disseminated or administered to respondents, or any tasks, experimental or in any sort of user study where participants had to textually answer open-ended questions as questionnaire tasks. So that allowed us to ensure that we included questionnaires, or excuse me, let me jump to the next slide. So what's important is we wanted to understand how to really contextualize the papers in our analysis. And so, we had to think, how can we ground what we are seeing from the papers that we are reviewing that have collected qualitative data in the literature and in a way that will be digestible or just could be easily understood by the community. So we actually defer to the qualitative research literature on quality and use rigor, because most of us here in attendance are going to be familiar with rigor and how that pertains to the conduct of research. So in the qualitative research literature, rigor actually just means a clear description of steps in one's research, but it's the components of rigor that we really wanted to use to contextualize the papers in our analysis. So whenever qualitative investigation is conducted, it can be considered rigorous when there is a proper utilization of theoretical constructs, data, samples, context, and data analysis processes. And it's actually encouraged as a language to dialogue with, let's say, quantitatively grounded research communities, best practices of qualitative methodology. So what that really did is we took all the papers that we saw that collected qualitative data and analyzed that data to really understand what are the theories or frameworks that they used, the qualitative methodological approaches, the qualitative data collection methods, and the qualitative data analysis processes. Now, this is actually just an excerpt from the table that we included in our paper of the papers that we analyzed. And so what we're depicting here are all those papers where some form of qualitative investigation was employed as part of a user study, along with those corresponding components of research rigor that were discussed in each paper. So as you can see, the most common method used was actually instantiations of the questionnaire task. And the underlying theories or frameworks that did inform the collection and analysis of qualitative data, those span various domains. So psychological, AI, and even human-centered computing. But what's interesting to note here is for many of the papers where a qualitative data collection method was used and interviewing was that method, the format was left unspecified. And even where coding was used as the data analysis process, the coding method was also left unspecified. And I've been trying to think for a while, what's a useful analogy to help kind of reinforce why it's important to specify interview format, or why it's important to also specify the coding method. And I like to liken it to conducting statistical analyses. If we think about a statistician or anyone who is quite familiar with statistics, looking at any sort of statistical analysis, and there are components that are missing, then naturally they may not be as receptive to the conclusions or the findings that are put forward that correspond with those statistical analyses. So that's why part of this analysis, the motivation was really to highlight what we can do to really promote that systematic collection and analysis of qualitative data in XAI. And I think this speaks back to the cross-pollination that has emerged a few times in this workshop. So naturally, this brings me back to those recommendations that I do want to leave everyone with today. When you think of conducting user studies, that you will in turn end up collecting and analyzing qualitative data. So again, if interviewing is a method that you do plan to use, please ensure to specify the interview format. And this also includes providing an overview of the interview guides that are used, those main questions that you ask, and really, clear representations of the data. So what are the data that supported your major findings, and even the data that contradicted your major findings? And naturally, we want to ensure to please be explicit with your data analysis processes. And
3 minutes, Adam.
okay, thanks. And any qualitative data analysis that you do perform, you clearly tie to your research questions. And for this third recommendation, the reason why I do focus on grounded theory, because that does tend to be one of the most widely known aspects of qualitative research. And we have seen it in a few papers as well, where those methods of coding that are part of the grounded theory coding canon are used to analyze qualitative data, but the actual grounded theory methodology was not being employed. So there's an important distinction to draw there. So you want to make sure to not claim utilization of the grounded theory methodology. And as I mentioned earlier, so the work from DARPA does, elaborate very nicely on this topic of how interviewing can be valuable to studying mental models in XAI. We also have seen some work to suggest and to pose to consider utilizing interviewing to further investigate the trusting process in XAI. So that's definitely a consideration. But yeah, finally, just really want to underscore to just please consider that collaboration with experts from social disciplines, really toward bolstering that rigor and effectiveness in the user studies that we do conduct in XAI. And the point is to really emphasize that, to maximize that cross-pollination, since XAI really is a nexus and multidisciplinary. So I'd just like to quickly acknowledge of course, all the attendees here, the co-chairs, reviewers of the workshop, and our funding source that actually allowed us to complete this work. So we're currently funded by the Biomedical Data Translator Program that is actually National Institutes of Health program at the National Center for Advancing Translational Sciences. So with that in mind, are there any questions or comments?
Thanks, Adam, for the wonderful talk. I think we have around 30 seconds for a question. If anyone has.
I've got one. Thanks to Rosina for suggesting it. So Adam, I'll put you on the spot. So there have been several people who have suggested ways to teach computer scientists how to conduct user studies or have certain messages for them. How does yours relate to what else you've heard in the workshop so far?
So, I think it does definitely align quite a bit with what Margaret was saying this morning. And I think that it's important just to make sure that if you do not have the time or the resources to make sure that every user study that you conduct, that you can collaborate with somebody from a social discipline, just to really dive into the literature and making sure that you do follow whatever guidance has put out there. And that's why I really think that statistics is the perfect analogy, because you can have a statistician look at work or any sort of statistical analysis that's put forward in any other domain, and they can easily dissect it and see, okay, did they use the best possible test for the type of distribution of the data or so on. And I think it's, again, very analogous to what we're doing here with qualitative data.
Okay, thank you.
Thanks, Adam, again. Is Mara available? The next talk?
Yes, asking to share the screen. I'm not sure this is working. Can anyone see my screen?
We can see your screen, but not the slides. I think the other screen, you're seeing the.
Yeah, okay. Can you see the slides now?
Yeah, no, it's visible.
Yeah. Okay, great. Oh, sorry.
Over to you,
Okay,
Mara.
so, okay. Hi, everyone. My name is Mara Graziani. I'm a PhD student at the University of Geneva and at the University of Applied Sciences of Western Switzerland. I mostly work on interpretable AI for medical applications, and I would present our latest work on the evaluation and comparison of scene and visual explanations for histopathology. I would like to acknowledge the people that contributed to this great work, particularly Thomas Lumpec, who took care of great part of the experiments, and also Vincent and Henning, who supervised the screen creative device. So I guess that all people here agree that machine learning models are not always transparent in the decision making. Particularly, deep learning methods are perceived as opaque and as black boxes. Now, as developers, we use explainable AI for different reasons. So we debug our models, we get insights on the learning mechanics, we check for biases in the data and eventual confining filters. We also use these explanations to justify the model predictions on specific inputs, and finally convincing ourselves that the model is working as we expect. But we also know that not all circumstances are equally easy to explain. So if you have already paid attention to the picture on the right here, you might wonder, why is this picture here? And well, let me say that it's exactly because it represents a set of circumstances that is quite tricky to explain. So similarly for us AI developers, some applications may be more difficult to explain than others. And depending on the application domain, the requirements for explainable AI may differ and may need some tuning. So before getting to the technical details of our contributions, I really wanted to underline that there is little point in generating misleading explanations, not even if these explanations may convince us that the model is doing what we expect. So to drive our developments in explainable AI, we should evaluate the explainers and see if we can do any better than what we already have. So finally, I take the occasion to agree with what has been mentioned several times already during this workshop, that is, who are we addressing our explanations to? So are we considering who receives the explanations when we develop these methods? And I think that this is kind of essential to generate useful techniques. Now, particularly in the medical domain, the application of AI is a very sensitive spot. When analyzing human tissue for cancer or inflammatory diseases, pathologists are legally responsible for their decisions. And because this influences like the treatment planning and finally the life of the patient. So imagine the impact of a not needed chemotherapy because of a cancer that was wrongly diagnosed as invasive. And you see that this has a great impact on the life of the patient. And there is an impressive amount of work in artificial intelligence for histopathology in the literature. But because of these high risks in the decision-making, the deployment of such algorithms in clinical routines is rather cumbersome and not really legally possible. So explainability has the potential of broadening these perspectives in this domain, so applying AI in this domain, but a few parameters should be respected. So the explanations should be useful to the clinicians. And to be useful, they should be concise, appropriate to the domain. They should not be redundant, for example, overwhelming the clinician with information that is not really relevant to the case. And relevant information is what generally leads, in fact, to action that might have a clinical impact, such as asking for further checks or doing another analysis. Finally, the consistency of the explanations is also as important as the reproducibility of our machine learning experiments. So with this in mind, we set the objective for this study, that is to evaluate the most popular visualization methods for histopathology images. Now, as opposed to the domain of natural images, histopathology images present some challenges for visualization methods. Visualization methods in general are very easy to evaluate qualitatively for natural images, but they become non-trivial to evaluate on histopathology. And especially if we want to measure the qualities of domain appropriateness, consistency, and usefulness of the explanations that I just discussed. So we decided to try and do this anyway, and we came up with a framework that makes us use nuclei annotations to evaluate quantitatively the visualizations. We took our network, an Inception V3, that takes us input images, images of tissue fractions at a very high magnification and predicts whether there is tumor or not in these images. So to train the network, we use two publicly available image collections, the Chameleon and the PanNuc dataset. The PanNuc dataset in particular has nuclei annotations for 5 different types of nuclei. So depending on their functionality within the tissue, the nuclei are annotated for belonging to either inflammatory or neoplastic or connective, epithelial, or dead cells. So we have really an entire map of what's in the image. Now, as a disclaimer, I want you to focus over the remaining part of the talk on neoplastic nuclei, that are those that are signaled as red in the images, because these nuclei are those that are indicative of presence of tumor in the tissue. So given this classification setup, we then generated class activation mapping and local interpretable model agnostic explanations as visualizations for our classification model. These two techniques are the most cited visualization methods in the literature. And it is so because they are intuitive to understand, they are very easy to apply, and they reported impressive results on the domain of natural images. Now, if you're not familiar with these methods, don't worry, because I will give anyway a quick introduction in the next slides. So in this picture here on the right, I am showing what the output of these methods looks like when you apply it on our histopathology images and on our model. And I'm showing the output for some correctly classified images and for some misclassified ones. We can see that the class activation based methods activate where the red nuclei are, so the neoplastic nuclei, for correct classification. Line visualization require a bit more of effort for the interpretation, particularly with this heat map. But in general, blue areas are showing, are highlighting and are showing where the activations are for non-tumor, and the red areas show indicators of tumor, while the green areas are actually showing unimportant pixels. So red areas are those indicating tumor. And so also just to clarify our goals, given these visualizations, we wanted to evaluate their appropriateness to the domain of histopathology imaging, the inter-agreement of different techniques, and the consistency and reliability of these visualizations. And to do so, we computed two metrics previously used also in the literature, that is the intersection of a union of the heat maps and the different nuclei annotations, and the structural similarity index between pairs of heat maps. So the first technique we evaluated is local interpretable model agnostic explanations, also known as LIME. In this method, an intelligible surrogate model, that is generally a linear classifier, is used to approximate in a neighborhood of a data point the decision-making of a black box model. So the first step when using LIME is to divide our input image in superpixels. Superpixels are regions in the image that are obtained by grouping together the input pixels by their relative similarity of intensity, their texture, or contextual information. These regions are then used to generate perturbed versions of the image that will define a neighborhood and the space of your decision function. So in this example here, the neighborhood is defined by the samples falling in the yellow area in the image on the right. The decision function of the complex model, let's say a deep neural network, is the line in gray. And this decision function is approximated locally in the yellow neighborhood by the surrogate model that is, in this case, a linear classifier. And this surrogate model is then used to establish which of the superpixels contributed against the classification as one class or the other. So for the experiments, we tested the two image segmentation algorithms that are quite common. There are the simple linear iterative clustering algorithm and the 1012 algorithm. As for the second technique that we analyzed, this was class activation mapping. Now, I expect several of you to be already familiar with this technique, so I won't go too much in the details. But in brief, what CAM heat maps do is that they give us an idea of where the network is looking at to make the decision. And this is obtained by aggregating the feature maps as a weighted sum operation, where the weights are given by the global average pooling layer before the final softmax. We tried different implementations of CAM, for example, the classical CAM, gradient-based activation mapping, and GradCAM++, that is an even further specialization of this technique. So our contributions in this paper are essentially what we are able to see with our evaluation. And the first thing we noticed is that different explanation methods rarely agree. So if we focus here on the bar plot in the black box, there is the evaluation of the explanations for correctly classified positive samples, so images containing tumor cell. And you can see how low many of these bars go, showing that most of the methods actually attribute the positive outcome to different areas. The only couple with high pairwise structural similarity scores is that of CAM and GraphCAM, that is in light past the green. And this makes sense because these two methods were shown to be actually equivalent up to a normalization constant. But for all the other methods pairing, the scores show quite some disagreement on the positive cases. Now let's keep in mind that the main task here is the detection of images of human tissue containing tumor. So the lack of agreement of multiple explanation is an issue because we may want to use them to guarantee objectivity in the decision-making of the network. For example, stating that there are atypical nuclei cells in a specific area of the image. Our second contribution was evaluating the attention of the network on specific nucleotypes according to different explanation methods. So to do this, we started by thresholding our heat maps so that only 60% of the highest values in the activation maps was kept for all images. And we then computed the intersection of a union between the nucleotype segmentation masks in the pan-nuc dataset and the thresholded heat maps. And we can see that the highest value of the intersection of a union correspond to neoplastic nuclei that, as I mentioned before, are actually the ones that are most indicative for the presence of tumor. And this may be quite comforting, but it might also be due to the distribution of neoplastic nuclei in the pan-nuc dataset images, so to the underlying distribution of these type of nuclei in the data. And it might not be due instead because the network is actually learning to use these nuclei to drive the decision-making. And when we thought this, we decided to compare the intersection of a union that we obtained for a trained network to those obtained from a network with randomly initialized weights. And we saw that there is actually no significant difference between a trained network and a not trained network. And as a final contribution, we proposed some consistency and repeatability analysis. So as I mentioned earlier, LIME is a perturbation technique that requires the generation of superpixels and of perturbed images. So the number of superpixels and the number of samples included in the locality of an input, so the number of perturbed images, are two hyperparameters that need to be tuned. And we analyzed the structural similarity between heat maps generated with different values of these parameters. So in the first plot in the upper left here, we're showing that we need around 100 superpixels to obtain solid explanations. And the second plot on the right is showing that the neighborhood size should be actually fairly large. So around 1,000 samples starts to be good. And as there is a certain degree of randomness in the generation of the perturbations, we also thought of evaluating the repeatability of the heat maps for the two different neighborhood sizes of 100 and 1,000, and for multiple numbers of superpixels. So for instance, we checked by recomputed line with a different seed if we obtained consistent heat maps. And from our results, if we maintain a fairly large number of superpixels, so let's say 100, we do not get repeatable explanations. And the repeatability becomes even worse if more pixels are used. So in conclusion, in this work, we evaluated the following properties of the most cited XAI techniques on histopathology task of binary classification of tumor versus non-tumor. So the appropriateness, we evaluated the appropriateness by the intersection of a union with different nucleotypes. We evaluated the actionability of the explanations by evaluating their non-redundancies, and we evaluated their consistency by checking repeatability and consistency around parameter shifts and doing randomization tests. The takeaways from this work are that the sole qualitative inspection of explainability outcomes can be deceptive. So for example, CAM and LIME have great value for model debugging purposes, but more metrics are needed to guarantee that these are really, that the model that we are trying to analyze is actually trustworthy. And the instability of LIME largely depends on the superpixel choice and on the post-processing of the heat maps. So I just think that at least in histopathology, current explanation methods still have limits, and there is a lot of room for relevant work towards stable, trustworthy, and reliable explanation. And if you're interested on this problem or working in this domain, I invite you to have a look at the GitHub folder and to reach out for discussion. we're still perfectioning this evaluation method, so we're really eager to know what you think about it. And this is the end of my presentation. I will now be available to answer any questions if there are any.
Thank you, Mara. Thank you for the talk. Are there any questions?
So I have one. So Mara, thanks very much for your talk. It's nice to have an applications-focused talk like this. Given your conclusion, as you show here, I'm wondering whether you have considered developing your own XAI techniques that would be more appropriate for histopathology, and if so, how far you've gotten along that line.
Yeah, so I actually did the reverse order. So the first thing I did, I developed a XAI technique for histopathology, and then I said, okay, but let's stop and look back a second, and let's try to evaluate it first. So I did develop a technique that is called regression concept vectors, and it takes inspiration from Bing Kim's TCAF method. Yeah, so essentially we decided to model concepts describing the nuclei morphology, so the texture of the nuclei, the size of the nuclei, and by using these as concepts, we realized that they actually have a they take continuous values, because nuclei size, for example, if you take into account the area of the nuclei, it's a continuous measure. So we extended their method from a classification method to a regression method, and we shown that it's quite useful for histopathology, but we also want to make sure that what we're developing doesn't bring us to confirmation bias. So we're trying to understand how to best evaluate whatever we have already and whatever we develop, so that we know what we are proposing. And so we're also looking into user studies to further understand what's the limit, what is missing, and what can we do.
Okay, thank you.
Are there any other questions? I think we have around 30 seconds. I had a question, a very small one. So if you are planning to do human studies, would that be, I would imagine that would be with experts from the medical domain?
Yes, definitely with pathologists. Yes, it's not easy to design a user study, and I think in histopathology might be even more complex, because it's a domain where there is a very specific kind of expertise that very often computer scientists don't have. So it really requires this intercollaboration between two worlds. And as I come learning now from the workshop, it's also relevant to introduce other people from other domains in the loop to really design a user test that is the most inclusive as possible.
Thank you, Mara. Thank you for the talk. Next up we have, so unfortunately, the next speaker is not available. Sushant Agrol, he couldn't come, but fortunately we have the speaker that was absent from the yesterday's session, Sheng, here. So Shen is going to present in this slot. Shen here.
Yeah. Can you guys see my screen?
Yes.
Cool. Yeah. I'm Shenmian Xu, and before I start, I want to thank the organizer for organizing the workshop, and thank you for accommodating the schedule. So I'm here to present our work on 1-versus-1 attribution using GAN-generated counterfactual baselines. This is a joint work with Pinju and Zohar. So imagine that we have a classification model, and we show the image, and the model tells us that this is a duckling. And one of the questions that we might ask is, what makes a duckling? So the model might come back telling us that, okay, look at the head, the eyes, the wings, the claws, they all point to the fact that it's a duckling. But then we might be confused, right? Because it pretty much just tell us all the features that are present in the image, so it's not super informative.
Okay.
So in order to make understand more about how the model brings to a decision, we might add something that's slightly different. We might say that, okay, this picture also looks a bit like a chick, so how do you distinguish this duckling from a chick? Then in that case, the model needs to be more selective, and it would really need to tell us the key features that will distinguish this photos from a chick, right? That might be just the neck, the beak, and the web feet. So that brings us to how we define the 1 versus all explanation versus 1 versus 1 explanation. So in our definition, we say that 1 versus all is the explanation is when we ask why does this instance belong to a specific class A, and whereas 1 versus 1 explanation is asking why the instance belong to the certain class A but not class B. In this work, we want to focus on the second part, 1 versus 1 explanation. And this is important because, as I mentioned before, many of the time, the 1 versus all explanation will just highlight a lot of features, and that doesn't really tell us how the decisions were made. And specifically, if we are interested in figuring out that why does the model make a mistake and misclassify the image that was supposed to be class A as opposed to class B, then that's where the 1 versus 1 explanation question can be very useful. So over here, we want to tackle this problem in using the attribution methods. And in the high-level attribution methods are a set of algorithm that takes the classifier S here and the input X, as well as a class of X as inputs, and it would output one importance score for each class. And I think that attribution methods, they're not new technology, and I just want to point out that if we look closer into the attribution methods, and most of them require some sort of reference inputs or a baseline input for making the feature perturbation. Even for occlusion, where it's what it did was to remove each feature and then calculate the impact on the end decision. And even for removing the feature from an image, it's also implicitly using replacing the feature from the value that comes from another image. Right. So in fact, all these attribution methods belong to the group of attribution global attribution methods that does the perturbation based on with respect to some baseline input. And based on the perturbation, it will assign some importance score to each feature. And because of that, if the original input and the baseline input has the same value on some of the features, then that means that no perturbation will be done here. And for most of the attribution method, it will end up returning zero importance score for those features. And this can easily be incorrect for many of the cases. And I just want to quickly bring to that. So in most of the attribution method, the default is actually either the zero value baseline or max value baseline. So that will be either white or black colors, and that would lead the attribution method to ignore all the area that were either white or black. So that brings us to one of the unsolved problems in the field, which is how to select a more correct baseline here. And next, I'll show you how this is related to our 1 versus 1 explanation problem. So attribution method has been used for like 1 versus 1 attribution explanations, and one way of doing that is to simply take the score difference of the score from the original class and the score from the target class, and we just take the score difference and then feed it into the existing attribution methods that will give us a saliency map. But if we give more thought into this formulation, it's not that hard to figure out that this is not always correct, because the second term here, like let's say if x is equal to the image that we are interested in explaining, then it should belong to the original cost, but not the target cost. That means the second term will be close to 0. And let's say if we are also using some sort of like blank baseline, then this term also wouldn't have much contribution here. So that means that it's the final attribution will be insensitive to the second term here. And as we can see in the results over here, that we're just plotting the saliency map from integrated gradient, deep live, and deep sharp. And when we change the different target costs, the saliency map actually stays almost the same. And that's the indication that the 1 versus 1 attribution that we generated based on this method is just not really working. So in order to solve that, we postulate that we can improve the 1 versus 1 attribution by picking a better baseline. And specifically, this need to be more cost targeted. It need to be depends on the target cost that we want to explain against. So we list out the 3 requirements for the cost targeted baseline here. The first one is, of course, that it needs to be, the baseline needs to belong to the target cost, as opposed to some random image. And the second one is that we also require the target cost to be close to the original input. And this is because if we don't have such requirement, then the baseline can be just any other image in the target cost, and that's not super meaningful. And third, we also require the baseline to be a realistic image. This is to prevent us from falling into any adversarial trap, and that's that even though it was classified as the target cost, but it doesn't look anything like that. So that if we combine these 3 requirements, we can write out the equation here that we are pretty much just trying to minimize the distance between the original input and the baseline inputs. And while the baseline input is selected from the realistic set of the samples within the target class. We can also look at a softer version of that, where we have R, which is a discriminator that distinguishes whether X tilde is the realistic image, and S here is the trend classifier that we're trying to explain. So we want to use GAN to generate the baseline instead of just selected it from the existing set. And specifically, we're using StarGAN over here. It's one of the image-to-image translation algorithm. What it does is that it creates different mappings between different image domain. Like cell transfer is one of the popular use case of that. And in the high level, what StarGAN does is that it has 2 parts of a discriminator. There's a source discriminator here that tell us whether the X is a real image or not. And there's another cost discriminator here that tell us which class does the sample X belong. So the discriminator is just trying to optimize the regular adversarial loss as well as the classification loss on the real images, whereas the generator here is trying to also optimize the adversarial loss in the reverse direction, and also the classification loss on the fake images, as well as some sort of reconstruction loss. This is to make sure that after 2 operations, we will have the image coming back to the original image. So to make sure that the original image and the transformed image look sort of similar. Right. So now, if we have the StarGAN equation over here, and when we compare it to the baseline requirements, it actually looks very similar. And particularly the adversarial loss is quite similar to the second term over here, whereas the classification loss is similar to that. The only difference is that these two terms are over here. So that means if we replace the reconstruction loss by the similarity loss here, then we will have a game model that is trained to optimize the baseline selection problem. And in reality, we are actually keeping the reconstruction loss because even though it's not very required for baseline generation, but we observe that empirically, it still helps the model to converge by a little bit. And here's just a diagram quickly showing how this works. And I'll skip the other option and just point out that B over here is the baseline generated by GameX. We call the method GameX, which is short for game-based model explainability. And if this is the input, what it does is that it tries to look into the parameter space for the realistic target cost, and then find the sample that is the closest to the original inputs. Right, so with the method established, I'm just going to quickly show you the outputs. So over here, we are considering 3 data sets, MNIST, the distributed house number, and CFAR10, and with the first column being the original inputs, and the second one is one of the baseline for the baseline, which is that we just simply select the image from the training data set, which is the closest to this input. And whereas the third one is the one that's generated by our model, GameX. So what we see over here is that when the data set is very simple, like MNIST, for example, it's fine to just look into the training set and just select something that's close. But when the data set get more complex with SVHN or CFAR10, it's like unlikely to find a good baseline, a suitable baseline, given this image. And whereas the one generated by GAN is much more effective on finding something that's close to the original image, but also belong to the target class. And when we feed these baselines, including the zero baseline, which is just a blank image, into some of the existing attribution methods, including integrated gradient, deep lift, occlusion, deep shop, we saw a consistent trend that GameX help a lot on making the salience map cleaner, in a sense of it is focusing on the key difference between that distinguish the original image from the target cost. Take the first row, for example. What makes this 0 a 0 and not a 6? It's really come down to just the top right corner over here and something that connects to the middle. And this is demonstrated with all the methods like when it was combined with GameX, which is here, here, and here, and here. And you can see a similar trend, like why this is a horse and not a deer. That's it's sort of trying to point out this area, which is where the stack should belong to, and why it's the car and not the ship. Like that's mostly the wheels, right? That's so it says like has some starting to highlight this area here. And we also test our explanation method on the binary classifier, which in which 1 versus 0 and 1 versus 1 explanation are sort of equivalent. And in that case, which I just want to show you that either the zero baseline or the max baseline these are the black and white color. They all failed when the background color is too different or too close to the baseline color. And the blur baseline, which is also commonly used, that they tend to pick up the contour of the objects. But in this case, we are trying to distinguish apple from oranges. So which it should all really be focusing on the color, not a round shape, because they are both wrong, both round. Right, and over here, I'm showing that it's showing how the 1 versus 1 attribution produced by GameX can be used for debugging the model. And what the question that we're trying to ask here is, why does the model produce the predicted label instead of a correct label? So take this one, for example, it thinks this is a 2 instead of 7 because of a tiny particle up here that's highlighted in the 1/1 saliency map. And if you look at some more complex examples, like this, it thinks that this is an airplane and not a ship because it's the lack of sea horizon, and maybe the front of it also looks more like an aircraft.
3 minutes.
Right. So, and over here, sanity check is one of the area that's like most of the attribution method has been failing. So it's a very, very simple but effective check that starts randomizing the model parameter from the top to the bottom. And what we expect is that when the whole model is completely randomized, then the saliency map produced should be also randomized. But that was not the case for most of the attribution method, as shown over here. And we show that with the help of GameX, like it was able to produce more randomized saliency map, and with the help of the randomized baseline. And since I'm running out of time, I'm just going to skip all these and come to a conclusion. And so to conclude, we propose this GameX is a game-based method for generating the model for generating the baseline for attribution method, and it can be used with most of the existing saliency map to improve the attribution outputs. It also produce more correct 1/1 attribution, like compared to the existing methodology. And as some way, it's also a method for generating the counterfactual explanation, because the baseline requirement is actually quite similar to what was used for counterfactual explanation. And with that, I conclude my talk here. And thanks everyone for listening.
Thank you, Shane, for the very interesting talk. Are there any questions?
Yes. In fact, more of a comment. We also had the presentation yesterday. I'm not sure if you saw it. Also talking about the baselines of feature attribution methods. I just wanted to, and it seems you're targeting to pass the sanity checks from Adebayo et al., right?
Yeah.
I want to suggest that you look at the work of Alan Fern, F-E-R-N, because he gave a talk at the HCAI workshop in Explainable AI, and he conducted other experiments that show more problems with feature attribution methods. And also there was a paper at the main conference, AAAI, which is called Hydra. And that paper not only used instance attribution, and also was a kind of an intrinsic method, but on top of that, it uses the whole trajectory of the learning. So I think that would be important for you to compare your approach with those now.
I see, interesting. Thank you for a suggestion.
Sure. Thank you for your talk.
There are any more questions? So next up I think we have a long break for 20 minutes. But if anyone else has questions for Shane, please feel free to ask here or even in the chat. After the break, we have a great panel, a cognitive science panel with Malay, Augusto, and Wal. So please join us after the break in approximately 20 minutes.
So if you don't mind, I'll just put this up for now. So this is an advertisement for who's going to be our panelists. And I hope that everybody can come back in just a few minutes, and this should be a great final way to finish up the workshop. Thank you. Bertram, thanks very much for joining us for this. We'll start. few minutes.
Yes, I'm really here. Just want to affirm that.
Greatly appreciated. Thank you.
Should we do a quick check of screen sharing slides?
By all means, go ahead.
Okay, let me do that.
I think I can see it.
You can see it, good. That is my sharing test.
I don't know if Eric and Denise would like to do similarly.
I like to play it a little loose. In fact, I was just going to suggest we just swap slides and just go for it and see the best,
That sounds great, Eric. That sounds great.
Works.
No.
I've actually done that once. That was very interesting to do. Denise, I'm sorry.
Yeah. Okay. You want me to try?
Go ahead if you'd like.
Bingo. Can you guys hear me okay?
I can,
yes.
And saw your slide momentarily. So
yeah.
Eric, I remember one time innovative program manager asked different PIs to present the other PI slides. And I wound up presenting Ken Forbes's slides. I think that what's the phrase when you swap and you tend to get higher quality? Well, that's what happened to me that day. So I was very fortunate. Now,
cognitive dissonance.
Yes, that.
Yeah, that's a good one.
And I assure you, I did not do nearly as good a job as he would have at presenting them. But boy, it was a pleasure. So that was fun. So I have so much tremendous respect for him. So.
Yeah, it takes a special person to be willing to try something like that. That's about the most. I think that is only second to like presenting in your underwear as far as like a phobia that most people would have.
That was
I
a joke.
won't do the underwear thing, but I will do the switch thing.
That joke, Eric, is one I remember from long ago, in which I think Pat's still on the line here. A colleague of mine, Rogers Hall, was a PhD student, and he got up to the microphone and he was mumbling something, and he didn't realize it was being picked up. And what he mumbled was, "Well, it's just like I imagined, except that I have my slides and my clothes are on." Or maybe just the inverse of that, I forgot.
Yeah, right.
But he intended to say this to himself just to get himself a little bit loose. And he was hot mic'd, so to speak, and they could hear him and they just laughed at him. And so he had them in the palm of his hands right to start.
I was just going to say, he broke the ice pretty well, it sounds.
Yes, and such a talent, didn't need to do that. So he's had a terrific career. So, okay, so it's now 5:05 Eastern time. And if you don't mind, we'll start now. So let's see, Sylvia was saying that this may not show up as well as it ought to in terms of being full screen, but hopefully you can see in sufficiently large font that I've got one slide here, though not in, well, I guess I can temporarily put it into display mode. And on the slide here, I'm trying to indicate that we've got a terrific lineup for our second panel. And the topic of the panel pertains to that of the cognitive and social sciences and their relation to explainable agency in AI, which is the name of this workshop. I'm happy to report, or perhaps unhappy to report, to Eric and Denise and Bertram that we've had some discussions on this topic already. They were repeated by folks such as our presenters yesterday, including speakers Ofra Amir and Tim Miller, as well as Shane Muller today. And I know Pat Langley touched on it in his presentation. And by golly, there were others as well. Well, Margaret Burnett gave the early presentation today. So there's been some discussion on the topic. And in some cases, people were talking about their own research, in other cases, more generally speaking. So I'm happy to report that we've got three top-notch people here who are going to help us out here, Eric, Denise, and Bertram. And I'd like to ask you to go ahead, please, and just introduce yourselves briefly. And I'll be happy to stop sharing for a moment so you can do so. Eric, would you like to say a few words about yourself?
Sure, thank you. My name's Eric. I'm a naval officer, a scientist in a uniform. I work with David at the U.S. Naval Research Laboratory. My background's in human-computer interaction with an emphasis on computational modeling. And I work primarily in the areas of human machine teaming, autonomous systems, trust in AI. And those are the sort of areas that I focus on.
Thank you. Denise, would you like to introduce yourself?
Sure, I'm Denise Augusto. I'm professor at Drexel. I'm also the director of our Masters of Science Information program. I study information behavior, and my particular focus is on kids, but I won't be talking about kids today.
That's right. I saw that you had an Explainable AI kind of publication relatively recently, so it seemed like a good choice. Bertram, would you like to introduce yourself briefly?
Sure, I'm Bertram Male. I'm at Brown University in the Department of Cognitive, Linguistic, and Psychological Sciences. We're still the longest name, but I think one department is trying to make an even longer name now. So I've been trained in a little bit philosophy and linguistics as an undergraduate in Austria, and then in psychology in the US. Sort of got caught here, and in the last few years, also did some human-robot interaction work, collaborated with folks on questions of how to build some moral capacities into robots. And explanations have been a long-standing interest for me, really from the dissertation time on. I've been thinking about meaning explanation, especially explanation of actions. So I'm very excited about this panel.
Fantastic. I'm glad that we caught you. So thank you very much for be willing at a relatively late notice to join us. That's just great. Sure. So I've asked Eric, or rather I've accepted Eric's invitation to go first because he wanted to set some stages here. So Eric, I'm going to hand it over to you, and the intent is to give each of our panelists around 10 to 15 minutes to lay out whatever they like. I've given them some seed questions, the ones that I displayed earlier, but by no means should they feel that they have to stick to them. So with that said, Eric, I invite you to go ahead and take the helm.
Okay, thank you very much. So yeah, initially I thought that this talk would be much earlier in the week, and so I thought I'd take the opportunity to sort of like preface a whole lot to audience that may or may not know a lot about XAI. I think all of those assumptions were proven false over the last several days. So I did adapt my talk as much as I could. I have a lot to go through, so I'm going to kind of rush through this a little bit. But in real high level, I'm going to talk a little bit about the DARPA Explainable AI program, and its relevance to this talk will be pretty obvious pretty quickly. Talk a little bit about the concept of hybrid intelligence and why I think that's the direction that we ought to be heading in explainability research rather than some of the directions we've already been down for several years now. And then I'll just introduce really briefly a new neural network modeling technique called nodes. And showed very, very, very quickly some results of a study that we just finished, and we just uploaded a paper to Nature Machine Intelligence this morning. So that'll be the tail end. As I've already introduced myself, I'm a uniformed scientist in the United States Navy. I work at the Naval Research Laboratory with David. I do a lot of different stuff. This is the slide that we typically use to explain what the XAI program is at DARPA. And the concept is based around this argument that the highest performing models are also the lowest in terms of interpretability. And the argument is that there is an inherent trade-off, and you have to accept that trade-off. Now, this was pitched as a program at DARPA in 2015, the end of 2015. It was started in 2016. And I think in the ensuing years, there's been a lot of open discussion about the veracity of these claims. You don't necessarily need a more complex model to have more accuracy. That's definitely been demonstrated. And also some of the more accurate models are not necessarily intrinsically opaque. It just depends on what questions you're asking and what you're trying to accomplish. So I'll start with that. Because, as I may or may not have mentioned, I've been the lead on the evaluation team for the DARPA Explainable AI program for the last several years now. I've been knee-deep in every bit of the details as you can possibly imagine. And the overwhelming majority of the work has been done that's been very good, but it's really been done only to the benefit of a very small population. And the motivation for explainability has always been, at least at the face value, has always been to the benefit of the end user. And that end user may be a regulator, or maybe a company who wants to adopt ML. But it's always been the audience is this sort of non-computer scientist expert. But really, if we look at it, we've got a lot of work that's really only been focused on the outputs that can really only benefit people who really are intrinsically trained in machine learning. And even if you just look through the literature, as I've done in the last couple of weeks especially, there's just inherent disagreement, even on basic terms such as what is an explanation. And what people often will refer to as an explanation in one domain is very far from what I think the vision of explainable AI is in terms of, say, HCI communities of practice, or folks who are focused more on usability or making practical this thing called machine learning, or maybe even legal experts who want to actually see it to used in some large capacity, but in a fair and reasonable way. So there's a lot of these misunderstandings. And as I've also pointed out, the overwhelming majority of the outputs of explainability research over the last several years have really only benefited a very small population. And if you look here, these are the top 3 approaches to visual saliency, or approaches to explainability, which are essentially visual saliency. And although these 3 at the top here are very different from one another in terms of what's going on, how the model is being promulgated, how it's being looked at, how it's being modeled, and whether or not it's a secondary model or primary models, things like that, the end result to the uninitiated is essentially the same thing. There's very little that you can really learn from what's happening here. And there's not really many answers to any of the questions that at least the customers that I have to deal with on a daily basis are asking for. And as you see here in the bottom one with the Husky, you know, the benefit of something like visual saliency is very, very, very limited in terms of what it can actually tell you about what's happening. As you see here, the same explanation for why it's a Siberian Husky is also why it's a transverse flute. It doesn't really give you very much information. And I think there's been this inherent tension between what is the purpose of explainability. And like I said, most of the time, at least at face value, the purpose is we want machine learning to be accepted. We want it to be used. We want to avoid another AI winter, or we want to avoid going down the path of, excuse me, the expert systems era, where they were praised to be the answer to all decision science problems. But really, if you look, they were never, ever close to achieving the reality of what they could actually do. And they never achieved widespread adoption. So machine learning is really facing this very practical uphill battle. Can we get people to trust it enough to actually use it and plug it in? And can it do what it's supposed to do? I think it's valuable to kind of look at and examine ourselves at a philosophical level at some point, because I think sometimes we're still trapped in a very old metaphor when it comes to talking about AI. And that is this concept of creating like an artificial human being, or an artificial brain, an artificial reasoner, an artificial decision maker. And if you look at a similar pattern, for more than 100 years, people were looking at birds and trying to figure out how birds fly so that we could figure out how we could fly. And if you look at the skeletons side by side, you can see why that's an obvious choice. The skeletons look almost identical to one another. But of course, us trying to build machines to fly based on the dynamics of birds really never got us anywhere. It was only until a couple of brothers from North Carolina came along and started thinking about things in a different metaphor in terms of natural physics that we were actually able to break free and really realize that potential. And so I commonly try to argue that the way that we think about AI is often in this very old Turing sense, which is creating this artificial human being, this artificial brain. And as a result, we're constantly going after this optimal design, optimal accuracy. Accuracy is kind of the gold standard of everything. But I think a more useful way to think about it is AI is something more like an orthotic, like something that can augment my natural ability in some practical way, or something that can make up for limitation in my abilities. The glasses that I wear on my face augment my eyes' natural ability. And if you think about it that way, then the priority really quickly becomes, well, in order to make this orthotic really helpful to me, it has to be fitted, it has to be comfortable, it has to be usable, it has to be something familiar to me. You know, there's a lot of ways that you can change the way we think about things. And that's kind of what brings me to this concept of hybrid intelligence, which is really this goal really ought not to be create this super accurate machine learning that's going to take over decision makers or replace decision makers, but rather how can we build this capability that can blend with human capabilities in a way that has synergy, in a way that the results, the performance is better than either the best human or the best computer alone. And that's really the concept I think that I try to look at. And the reason I'd say that is because thinking about it in that sense really changes our priorities and really changes how we go about, you know, exploring this. If you look right now at the literature, the overwhelming majority of XAI is looking backwards. It's always looking back. It's explaining what just happened, why it went wrong. It's always retrospective in focus, but almost nothing is geared toward helping me decide when I come to a fork in the road, which way should I go? When I don't have the benefit of ground truth and I have no way of validating the model, I have no way of looking at it and say, that is right or that is wrong, but rather, do I go right or do I go left? What do we have to help make that type of decision? Considering that machine learning's 99% of its value is found in its ability to make predictions, we ought to be focused much more on forward-leaning explanations. Why should you trust it? Why should you be, you know, willing to do something? From the field of physics, we have this concept of horizon of predictability. It's basically this theoretical point after which you can no longer make accurate predictions because the accumulation of errors over that time. And humans have, of course, a horizon of predictability that's much nearer, of course. You know, we're historically very poor at making predictions. You know, just look at, say, for instance, the last 15 years of economic predictions. This just came out in the New York Times yesterday. Or if you want to look at the 2016 presidential elections, you know, just dramatically wrong projections in terms of polling information. So I like to think about the real value of machine learning, and the real reason why we ought to be working toward explainability is to try to narrow this gap. You know, we've got this orthotic that can help us project far out beyond our own capabilities. But right now, the limitation is not the accuracy. It's not how far out it can get, but it's the unwillingness to use it. It's this reluctance to trust it because it's in a format that's foreign to us, and it's using reasoning that's foreign to us, and it's not well explained to people who are not specifically trained to understand and appreciate things like probabilities and other things like that. So that's kind of how I approach this concept. As a really quick, you know, maybe primer of one inherently like more usable way of going after explainability is to use something like neuroordinary differential equations, or nodes. Nodes are kind of a new thing, or newish thing. It came out in 2018, kind of hit the streets in 2018. 2019 is when most people started paying attention to it. There's a paper of the year at NeurIPS 2018, I think it was. Very interesting way of processing data that affords you several things intrinsically about the way that the model is actually built. Outperforms RNNs, but also works really well with irregularly sampled time series data, and gives you this kind of magic ability to look both forward and backward and perturbate the model in a way that you can actually understand what's happening. And you can track and understand the evolution of a process and the evolution of a prediction in a very detailed manner that doesn't take, say, you know, a master's in computer scientist. So we just recently ran a study, very interesting study. We took the Mimic2 database from MIT's 56,000 ICU patient records, very, very, very noisy, very messy, real data. Using our approach, we replicated a study and demonstrated that we could predict mortality. With only 48 hours of data, we could predict mortality out to a week with very high accuracy, but most importantly, was the results were very intuitive, very easy to understand. If I had more time, I'd be glad to take you through all of those results, but I'm already kind of running short on time here. So neuroordinary differential equations are just one example of where we might already have a good enough solution. We don't necessarily need to, go after this hyper accurate, super deep learning and then build on top of it another learner and another explainer on top of that and just continuously make a complex thing more complex, where the explanation ends up to be actually more difficult to understand than the original model itself. I think we have a lot more practical steps that could be done to make machine learning something comfortable, something usable, something approachable, and something that people are going to be more comfortable using, whether or not we ever get to the point where they fully understand. Let's not forget, right now in the world of chemistry, we do not have a full mechanistic model of why Tylenol works to help with pain, or penicillin with some infections, or lithium with bipolar disorder. We have a whole host of things that we don't fully understand ourselves, but yet we feel comfortable trusting and using. So I like to say it's a much more valuable use of our time to go after explainable techniques to look at the outputs, the form of those outputs, the way that we represent information. Its effect on human cognition is dramatic. I think the current sort of model that we're in, the sort of metaphor that we're trapped in, I think is only going to keep us in this kind of non-productive state. I think we have to think about designing for human beings, and that being the focus, the center focus, this usability should be central, not just developing more accurate models and other things like that. And finally, nodes are kind of a neat new thing. If you haven't heard about them, I've got all the references here. You're welcome to look them up. Kind of neat. And if you want to read the paper, we've got it up on archive already, and we've uploaded it to Nature Machine Intelligence. So good luck for us. So I have probably run over time. I'll stop sharing. And if there's any questions, or if not, we can take them afterward.
Thanks very much, Eric. I'm going to let Denise and Bertram go first unless there are very some strong clarification questions. But I suggest that we go right to Denise. So go ahead, Denise.
Okay, hi everybody. I'm Denise Augusto, and I'm going to exactly take up this idea that Eric just had of designing for humans. Okay, Denise Augusto, and I'm at Drexel. Many of you know Rosina, we work together. So my area of research is information behavior, and I want to discuss how information behavior might help us in XAI work. Information behavior is a subset of library and information science. It's a very multidisciplinary area. We borrow theories from education, psychology, HCI, and social computing. And here's a standard definition of information behavior that we get from Wilson. In essence, in information behavior, we try to understand users, how users interact with information systems, and any kinds of information technologies. I should point out quickly that we as a field cannot quite agree on what to call ourselves. There's a vociferous argument over whether it's information behavior, human information behavior, or information practice. If you're interested in a discussion of these different themes, you can see my paper that I listed here. Many of us prefer the terms information practice because it focuses on the sociological and contextual factors of how humans interact with information systems. But regardless, we'll talk about information behavior today. Now, how can we connect XAI to human information behavior? The basic idea here is that human perceptions of information can play a large role in the use and trust of systems-generated explanations. That the correctness of explanations alone does not guarantee target audiences will use or trust them. I think this is basically what Eric was saying. And if XAI researchers and designers understand human information behaviors, they can create systems of higher value and use to users. If you're interested in some of the human-centered work in XAI, Adam, Rosina, and I wrote a paper that you can see here that Adam presented just about an hour or two ago that discusses some of this human-centered work. Well, again, implications for XAI. Here we see a shift in the focus from systems optimization to optimization within context of human use. And I have a feeling that Pat's going to say optimization has not been a focus based on previous comment. But the important point here is that when we think about human information behavior, the goal of a system is not to generate the best explanations, but to generate the best explanations for intended human use within context. And context is a very big theory and idea in information behavior. Our interactions and preferences for information and information systems vary as context varies. So in 5 minutes or less, some classic findings from the field of information behavior. Well, a really early classic paper in information behavior is Robert Taylor's 1968 paper. And Robert Taylor discussed how people become aware of an information need. He said, when we first have an information need, it's just an inkling, just a visceral need, a sense of uneasiness. As we become more conscious of aware of that we need information, we have an ill-defined awareness of some kind of need for information, but it's still not fully formed. As we understand our situation more and our information need becomes more concretized, we have a more formalized understanding of our information need. Then users can describe needs in concrete terms and can make their needs explicit. It's at this point that users then turn to information systems to try to express their needs in information systems. And from Taylor, we learn that there's always a compromise in the information need, in the language used for understanding the need within the human's head to putting language into an information system. We call that the compromise in language. Other major findings in information behavior that I think are applicable to understanding users in XAI extend beyond theorists and beyond different decades of information behavior. 4 basic principles. The first is that humans want information that is most easily accessible. And this just makes sense. Humans are rational beings, and we want to maximize and save our cognition, our physicality, and our time. Secondly, we know that humans like familiarity. Habituation and familiarity are core principles of human behavior, human behaviors. People like display, use, and access to be the same across information systems as much as possible because that reduces constraints of cognition, time, and physicality. Thirdly, we see a long history of humans turning first to other humans when looking for information, and second to information systems. This is somewhat changing with the increase in facility and ubiquity of web-based information. Yet still, we see across demographic groups a strong preference for humans to get information from other humans first. And fourthly, we see humans like information that fits with existing mental models. For this reason, when we think about explanations, we want to try to provide explanations that can fit into humans' mental models. And this goes back to that idea of familiarity and habituation. Another paper I think of interest to the XAI community is Rhodes' 1986 discussion of characteristics of information needs. Rhodes suggested that we have these 5 main dimensions on which information needs vary. The first is importance. We have needs that must be solved right away. We need quick information, or we have needs that are deferred and the user can take a longer amount of time to gather and interpret information. Next, we see frequency, information needs that recur versus those which are new and more ephemeral. Predictability, anticipated information needs versus unexpected. Complexity, easily resolved solutions versus very difficult problems. And fifthly, causation. These are information needs that are either external or internal. This is of particular importance in work situations, very often in which we find the person using a system is not looking for information on his own, but rather as a proxy user. Somebody else has the information need, and it is being translated into a proxy user who then translates the information into a system. And going back to Taylor's idea, we see that the information need then is not compromised once as it's transferred into a system, but twice, because it goes from one human mind to another and then into the system. And in each case, we're losing some of the acuity of the known information problem. Another really key concept in information behavior that has strong applicability to XAI is the idea of cognitive authority. Patrick Wilson, in his classic 1983 book, suggested that cognitive authority is how we know the world. And we can know the world in two ways, either through firsthand experience, things that happen to us, or secondhand experience, things we read about, hear about, or learn about from others. And in Ray's paper, which is a very important discussion of cognitive authority, she suggested that cognitive authority can be operationalized as, quote, the extent to which users think they can trust information. This is very important when generating explanations. They need to be trusted by users across context. This means that cognitive authority is also closely tied to credibility. And going back to Wilson's classic work, he suggested trust in information, trust from others comes from either expertise or personal trust. Expertise being professional preparation. I, for an example, am a cognitive authority on information behavior. So some people trust me when I talk about this topic. But humans also have a strong placement of trust in personal relationships. For example, we tend to trust our mothers when they speak to us, not necessarily because they are our experts in a topic they're discussing, but because of the trust we place in our human relationships. Wilson further suggested that cognitive authority can also come from institutions such as universities or governments. Thus, users are more likely to trust explanations that come from perceived cognitive authorities, and that's something we want to express to users when we're designing systems. For a good discussion of trust in human-machine relationships, I suggest Hoffman's 2017 paper. So, main takeaways. Why are we talking about human information behavior and XAI? Human information behavior reminds us to focus on the value of explanations for users and within intended use contexts. It tells us to recognize that information needs evolve as users gain understandings of problems. It suggests we should understand factors that constrain user decision-making, limitations of time, cognition, physicality, and more. And it encourages us to recognize the role of cognitive authority in order to build user trust in explanations. And that's me. Oh, and if you're interested, a list of references.
Thanks very much, Denise. I anticipate that some people are going to be asking for these slides.
Oh.
So, okay, well, with that then, if I could invite Bertram to take the helm for a bit.
All right, let me share. I have to pull this up first. Here we go. And if all goes well, you see my title slide here?
Yes, I can.
Perfect. All right, so I'm going to tell you a little bit about parts of what Eric, I thought, was heading towards, but then the neural differential equations threw me a little bit. So let's see where we are meeting, and certainly also meeting with Denise. So I'm taking the workshop introduction text, and I'm going to just sort of run through some commentary. The workshop introduction says, Explainable XAI attempts to alleviate concerns of transparency, trust, and ethics by making AI accountable, interpretable, and explainable to humans. And this is pretty demanding. And so I'm going to work through a few important distinctions among the first three concerns, then some of the methods by which these concerns might be addressed, and then ask which humans are the ones for whom this AI is being made. And that's very much in line with both what Eric and Denise hinted at. So let's talk about ethics briefly. And I do not think that explanations, explainability, XAI can alleviate concerns of ethics. A perpetrator who explains his cruelty is no less cruel. There's only one way in which explanations could figure in the kind of direction of more ethical behavior, namely when the explanation is a justification, explains an action that at first glance might have been a transgression and unethical, actually turns out to be normatively accepted because it was done for the right reasons, for good motives, and actually trump any initial thoughts we had about why the person did it. But to address ethics and really the full-blown set of questions of ethical consequences of AI and robotics and technology, I think explanations play a very small role. Obviously, if you don't have any explanations and you're confused, that doesn't help much. But I think that ethics is sort of relatively far away. And that includes this very strong concern for fairness in AI. I also don't think that merely because we explain what the systems do and how they do it, that necessarily the systems become fair. But we can certainly challenge that in the discussion. Next was transparency and trust. Transparency I distinguish from explainability because transparency is more about seeing through something or seeing into something. And that's about knowing that it's doing something, what it's doing, and perhaps how it is doing it. And that's typically not the same as knowing why it is doing it. Knowing why doesn't also necessarily require knowing how. I might know why you say something, but I don't know how your brain does it. I'm not even sure how exactly you formulated the particular sentence, but I understand why you said it with just a few words of explanations. So explainability does not imply transparency and vice versa. Both of them are important, and if they're missing, then that could really mean obstacles in interaction with technology. But I think those two things really need to be kept apart. And trust, I think, is important to realize. Trust, and I'll try to show this on the next slide, actually incorporates transparency. To be trustworthy, among other things, is to be transparent, to be sincere, to be authentic. But trust is more than that. And we've done some recent work, and I'm going to give you just a hint of this work that tries to come up with the multiple dimensions that constitute trustworthiness. And in a sense, the evidence that people use to trust somebody, to accept risk in interaction with somebody and relying on somebody. What we did, informed by previous studies, we gave people a bunch of different words that were in the semantic field of trust and asked them to sort them in as many categories as they wanted, at least 2, no more than 6. And what we received with multidimensional scaling, k-means cluster analysis, or any other method you want, was a very systematic grouping into 5 areas of trust, if you will, or components of trust. And I'm going to simplify that by highlighting 4 of each of those. On the upper right side, you see competence, being competent, skilled, capable, meticulous. Then you see reliability, the classic automation dimension, predictable, consistent, dependable, reliable. That the word trustworthy sits right in the middle, and what you see in the right-hand side here is this transparency idea, to be candid, genuine, sincere, also honest falls in there. Ethical integrity, a little more abstract, principled, ethical, moral. And then there's something that is maybe part of ethicalness, but it falls out in also some work in business and organizational behavior, that bases of trust include this perception that the other one is considerate towards me, has my interests in mind, has goodwill towards me. And so what we see here is that these 5 dimensions of trust in different contexts may be differentially highlighted. An industrial robot, I mainly care about whether it's reliable or not. A machine that's a little more complex, I want it to be able to solve certain problems that it hasn't yet solved. And so I want some competence more generally. But when I'm interacting with a human or with a highly social robot, I'm beginning to also expect some other bases for trust. And some of the implications of that approach is that explanations might increase trust, because that's one of those motivators that is often given. Oh, we need explanations in AI because they will increase trust. Well, maybe. They increase trust when they provide some evidence among those 5 dimensions for trustworthiness, but that depends on what I'm concerned about. You may explain to me your competence, but really what I'm interested in is whether you're sincere, whether you are benevolent towards me. So you're giving me an explanation, but it doesn't actually meet my need at this point. Explaining by reference to capacity, standards, goals, or motives and norms would need to fall into, in a sense, the question that I actually had, my worry about, should I trust you or not? And if they are given in this way, referring to norms, they again are more justifications. I'm giving you my goal, why I do it this way, but still trust me because I have your interest in mind. So explanations, again, require a little more, and I get back to this topic of justifications. So explanations can increase trust in an agent's ethical integrity, transparency, and so on, if they provide the kind of information that we actually need at that time. Then there's the phrase of making accountable, making AI accountable. The word accountable, and you can go into the dictionary, has several meanings. Being explicable, that basically just means the same thing as explainable. Being required to explain or justify, that's a little different. You are accountable to me if you are required to explain to me whatever your decision might be. Even more, sometimes accountable is referring specifically to answering for one's transgressions. And answering for transgressions can mean being held liable. That is, I may have to pay consequences, compensation. I'm a proper target of blame. So you see this full range of, again, neutral explanation all the way to moral concerns here. And the question now is, if accountable really has this target of blame, this liability meaning, does that mean we have to make explainable AI fully morally competent? And I don't think we have to jump to that conclusion. Primarily when people want someone or something to be accountable, I think they want to understand, sort of as first level. They want to be able to criticize if they're unhappy with some output, some behavior. They want to be able to say how it should be done the right way, to correct and improve. And I think this fits very nicely with this forward-looking view that Eric proposed, where explanation is just the starting point. And I understand why you did this way, and therefore I shift your behavior towards something else, which might be more meaningful, and then I could trust you. Blame has sort of a bad rap, and I think that blaming in the best of worlds is criticizing, giving the person a chance to correct. And that's the meaning that I think accountable can carry. And actually AI and robotic systems are probably realistically buildable as having this ability to correct, to take criticism, to improve, without having full-blown moral agency. Finally, the core terms of XAI, interpretable, explainable. I think it's important to realize, and both Denise and Eric hinted at that explanation is an act for an audience. There's an explainer, there's an audience, and AI might either be the object that is being explained to the audience, or the AI might be the explainer. But what we have to realize is that there's no explanation without thinking about, well, for whom is the explanation given? And the simplest way is to think about explanations as being answers to questions. If I don't know what your question is and what you know, I don't know what answer I should give you. It seems so obvious once you think about it. And if that's really acceptable, then explainability means an AI is explainable if the explainer can explain the AI's behavior to designated audiences. But it's very, very different depending on who that audience is. And this is this concept from sociolinguistics called audience design, that we shape our speech, our style, and our content of communication entirely dependent on two things: what we try to express and who the audience is and what we think it expects. So an explanation should be shaped for its audience when the audience wants it, namely, for example, when they're confused, curious, or when they worry about something, and not constantly. An AI that is explainable and spits out explanations might be very annoying. It shapes the communication for its audience for what they are specifically curious, confused, or worried about. That means I really need to know the question that you have before I can figure out what my answer would be. There is some work on contrast cases. You did this rather than that, and that becomes the structure of the explanation. Or I have to figure out what exactly the piece of knowledge is that you're missing, and if I give this to you, then you understand. And not necessarily a long causal chain. You might need just one piece and everything is clear. And with the kinds of answers that the audience expects, it needs to be in a language, in a conceptual framework that is familiar to others. The conceptual framework of physics is very different from a framework of human intentional agency. Obviously, and this is, no strong criticism to Eric, but differential equations are not going to be the way to explain why a system does something if we worry about it or if we're curious about it. If the Question is, why did the car slide off the road? Oh, absolutely. That might be physics equations and weather and other reports that might help us answer. But why did you leave me lying there for an hour? And I might ask that the search and rescue person or the search and rescue robot. The answer is going to take into account information that is relevant to me. It includes motives, maybe good reasons, justification, knowledge, and facts maybe about me that I was younger and therefore I could probably be there on my own longer and the other person needed rescue more quickly. And those explanations are very different from differential equations or any other more physical language. I've written a lot about this, so here's just one book citation on this topic. And more recently, Martin de Graaf and I have a AAAI fall symposium paper in which we lay out sort of the theory of explanation that people bring to bear when figuring out human behavior and how we think robotic systems should probably also explain human behavior if they interact with us. So to conclude, explainability is really the ability to explain X, whatever X is, a machine, an AI, or another human, to an audience. And it doesn't matter whether it's a third person who explains or the agent, him or herself, or itself, in the case of a machine. We have to carefully select the audience. And as Denise said, it's very different whether it's an expert, ordinary people with some tech knowledge, or a suspicious older adult who knows nothing about this even cell phone, let alone social robot. All the person wants to know is whether the robot will stop annoying them when they haven't yet taken their medication, and how they can tell the system, I know, but I'm not going to do it before I've finished my task. Those are very different kinds of audience demands. We have to recognize that explanations are both cognitive and social. The information processing that goes into an explanation is as important as the recognition that it's a social act, that explaining it could be patronizing, could be careless. The social act takes into account what is actually needed for this audience. And explanations can increase understanding and trust, but only if they address the audience's confusions and concepts and answer what their questions are. In contrast to that, I think full-blown accountability and managing blame and ethical concerns are quite a bit further away. And I think we should not confound all those. There's plenty of work to do to get systems to be explainable for the right purposes without necessarily solving a lot of other challenges for technology. All right, that's my bit.
Thank you very much, Bertram. Thanks to all three of the panelists for laying out a whole host of ideas that make it very interesting as to where to even begin. I received a couple of questions, early ones from Pat, but Sylvia, would you like to go ahead and bring up what you recently shared with me?
Yes, so thank you all for the nice talk and contribution. Like all of you mentioned that there are different definition of what is an explanation and what is explainability in computer science, artificial intelligence community, and human-computer interaction community, as well as cognitive science and human factor community. And how would you mitigate these differences, or even better, how would you combine them? Because there seems to be like this incongruency that leads us also to different outputs.
Should we go in order? Eric first, then you second.
We can go whatever order you'd like. Go ahead, Bertram.
Well, I'm not sure I fully understood the question. Did you say, Sylvia, that there are all these different demands that we raised, probably now in some 8 to 10 to 12? How can we build systems that meet all these demands? Is this a correct interpretation of the question?
This could be one interpretation, in the sense that if there is this difference in the definition, this would be reflected also in a different output. And we should find a way to define the concept in a way that we can come out with an outcome that is clear, and it's what all the communities would like to or would define as an explainable system. because if from one side we have this focus on the human, and on the other side we have this focus on making the model, like yesterday there was Bin Kim saying, like the model should be should say what it is doing by itself, like should explain his internal working without exactly like without looking at the human as a final, so more as a property of the model, while when you define explainability, you define it as something that the human or the observer or the receiver gives to the model. I don't know if I'm explaining that well. So we should try to find a common definition, I would say, if we want to achieve an output that would make everyone happy.
So I usually don't think that a common definition is realistic. I think more realistic would be to say, hey, there are different meanings. Let's keep the meanings apart. And the meanings usually refer to goals that you have. One goal might be to just make sense of these crazy million-layer deep learning systems. That's a very different goal from saying, I want to understand why this robot's just rolled over my foot twice, even though I told it not to do it anymore. And we use the same term for often quite different, maybe slightly family related, but still distinct phenomena. And I think as long as, and I take this really to be one of Eric's messages, as long as we put all this money into one, if you will, definition of explainability or one set of goals, we overlook a lot of other goals. And I think Denise nicely laid out what we should take into account, and the goal of taking into account information behavior, tendencies, and maybe also pitfalls of humans lead to then very different solutions. So I don't think we need a common definition, but we just need to figure out what we actually want and what we care about, and then come up with the paths of solution that might be different depending on the goals.
Denise, would you like to contribute to this?
Well, as a humanist, I would always argue we don't want to forget humans, and that certainly we can have different definitions of explanation, but regardless, to me, an explanation doesn't really mean anything if it doesn't help humans. That's the entire point.
Yeah, and I'll just quickly add, there have been several papers that have tried to synthesize all of the literature and actually arrive at, say, common definitions across the board. Those papers are somewhat helpful, but I think I would agree with Bertram. That's not necessarily where I would put my effort in the same way. I think a better way perhaps to answer that question is something more along the lines of what is the intended audience, or what are the questions that we seek to answer. And as you pointed out, Sylvia, you know, a lot of folks do consider the explanation as more of a feature that's being outputted from the model, whereas other people consider it a property of the model. And that sort of supposes your audience. So I think there is a lot of reason why we want to have common ground, because that's why I put the table up that I put up. Not having that really leads to a lot of confusion. And in my line of work, if I've paid a lot of money for you to develop an explainable model for me, and then you put it in front of a bunch of lay people who have no patience for, anything, the results are not so great. And the results are they're going to find some other solution. And that's kind of the motivation where I come from. Excellent question. All right, Pat, I see you're like chomping at the bit to jump in here. Go for it.
Go ahead, Pat.
Okay, not really, but I don't like silence, so I usually fill it up. So I'm not sure if all of you heard my talk earlier today, but in it I made a distinction between what I called interpretive explanation, that is the construction of an explanation of, say, some external events, like you would do in plan understanding, and communicative explanation, which is once you've got this account, how you convey that to someone else. And I argued that explainable agency, as this meeting is about, is mostly about the second. and it's not that simple, but I wanted to see whether or not you agreed with that, in particular because Eric was talking about differential equation models of biomedical data. That sounded to me closer to interpretive explanation, and I just wanted to throw that out and see what you thought. And I'm happy to elaborate if my distinction's not clear.
Well, I'll take the opportunity to jump in. So you're absolutely right, and I'm glad that you kind of picked up on that. For me, so those terms are not terms that that's not the vocabulary that I would personally use, but it's still.
Well, I made them up, so it's okay.
So this trademarked Pat Langley, but you know, it's still very useful to consider. And I think the reason why I chose to go down the road of looking at nodes is because they don't require tremendous engineering, you know, after the fact. They don't require, you know, scaffolding and, you know, simulated models and all of these extra things to try to explain. And they're intrinsically understandable, but they also afford this different type of understanding, which is what, and if you go to read the paper that I referred to, that's sort of the other side of this coin. When I talk about the synergy, you know, the human brings something that we've never been able to model, and we probably never will, which is the non-conscious stuff that goes into decision making, such as intuition and creativity.
Of course we do. There's lots of work on that.
There is lots of work on that. There's still quite a bit of, there's a lot to be found lacking in those particular areas.
No question.
What I personally find promising about something like nodes or other models that are similar are that they afford the user to make sense of this information in a way that's more than just like a binary, like accept or reject. And so now you're getting layers of information that you can actually start to incorporate. And now you're sort of working with the system in a little bit more of a cooperative sense. And that's, I think, of much greater value. An explanation that actually adds to my overall understanding or takes me in new directions, helps me to look past bias and maybe broaden my horizons or my understandability.
Hey, it's okay. I mean, I work in both areas. Okay, so I'm perfectly interested in the generation of explanations of observed phenomena. I just don't think that that's what most of us mean when we talk about explainable agency. We're more concerned in that context about, given such an explanatory structure, how do we get it across to someone else? How do we decide what to focus on, what level of description, how to answer questions about it, not the generation itself, which is granted a challenge too. And if you agree with that, that's fine. They're both interesting.
I mean, they're not that distinct in the sense that they're part of a larger system. So Pat, you know something, you understand it, you realize that I don't understand it. So you use communicative explanations to transfer your model, if you will, to me, adapting to my already existing knowledge and building or helping me build an interpretive model of the phenomenon. And in a sense, this always cycles through, right? Like we come to an interpretive moment that we can then communicate to others to now hope that they will have that. And for the most part, we hope to get shared interpretive models as much as we can. So I think it's a good distinction because from a psychologist's viewpoint, different factors and variables will play in, but they're really part of a larger system. And it's only through this larger social communicative systems that we get grounded in our interpretive attempts. Because unless you just interact with physical reality, yeah, you might do this as Robinson Crusoe or whatever. But for the most part, we deal with complex events for which our socially reinforced and improved communicative explaining really helps. And this is what Denise really laid out very clearly.
Hey,
we go to other people to get explanations if we don't understand.
I agree with you. But I had an experience years ago when I was collaborating with a senior computer vision researcher, and he was brilliant. He had this great theory. It was clear he understood it very, very well, and he could not explain it to anyone, right? I mean, we know people like this. They're geniuses at the first kind of explanation and not the second kind, right? They can't get their ideas across. They're terrible. They're brilliant mathematicians who are terrible teachers, right? And yes, a complete intelligent agent will have both. I just want to make sure that, but I believe that in terms of designing, implementing, and evaluating AI systems, they raise different issues, and that we should keep our, figure out which ball we're trying to hit.
Denise, did you
want to add to this? Time.
I was just going to argue again, always as a humanist, that your differentiation makes sense to me because it goes back to the idea of compromised comprehension and compromised information need. As one person understands an explanation, another person will understand it differently. And this means every time that we translate from human to human or human to machine, there's either a loss of meaning or the meaning changes.
Are you saying that we should compromise, or that I am compromised?
I'd say that human communication itself is always compromised.
Pat, your example actually raises one of those challenges. So you describe this genius who understands this phenomenon, or at least we think the person understands the phenomenon. But if the person can't explain it, how much do we really trust them to then take the actions that may influence our outcomes? And this is true for AI, right? This AI system seems to be so smart. It's doing these amazing things. I have no idea how and why it does it. My trust, without an explanation that I can understand into my compromised mental model, that trust will be limited. And I think that's why the communicative part is so important.
I agree. I can't prove to you that he was really brilliant, but he seemed like it to me. I know actually what happened was, that I like to ask very focused questions, right? It was a very good relationship because he was low verbal and high math, and I could wring out the stuff from him. He had the answers in there. It just was painful to extract it, right? I felt like maybe I would have done well in the Inquisition era, and so yeah, I think he was, but I think we all know people like this. Some of us are.
Pat, I'm going to give a couple other people a chance right now. Thank you very much. Rosina, you brought up a point just a moment ago in chat. Would you like to elaborate?
About Shank's theory. Yeah, what Bertram just said is exactly Roger Shank's theory about the theory of understanding. That a person understands something fully when it has herself the mental model that is complete in their mind. Yeah, that was it.
There's actually an interesting, for some of you probably familiar, philosophical argument by Wittgenstein that there cannot be a private language, which means in some sense, I may have the illusion that I understand in a unique way, or I have a unique rule system, or I have a unique language. If I cannot share that with others, if there is no translation possible, it may not, at least according to Wittgenstein, be real. And that's where it's problematic if there is a unique, untranslatable, uncommunicable claim of an understanding. Because as a social community, not so sure we want to really trust that.
So I know that we've got one question that I'm sitting on, but I welcome the audience to bring up new ones.
I have another one.
Go ahead.
I didn't hear from any of you that I was able to capture, understand again. When you're talking about trust, anything that I read in Hoffman's work, I believe, about the fact that if I know when the system is not right, that helps me trust it more. So it's not that the system has to be perfect for me to trust it. It's just that I share the mental model to the point that I even know when it does not work.
I actually just am working on a grant proposal trying to make a case for this counterintuitive prediction that violations of rules or norms may lead to more trust than perfect reliable behavior. And not necessarily, but can, in the sense that that violation of an expectation of a rule, of a norm, gives the system or the human a chance to justify why they did it. And if they justify in a way that is acceptable to me, I get two pieces. I get an explanation and I get evidence that this system shares the same norm system that I have. And therefore, in the future, it will likely act on that shared norm system. I wouldn't have figured this out necessarily if the system had just operated reliably without error, because I might have stopped paying attention to it. So there's a way in which the right amount of sort of tension, if you will, contradiction, surprise, and sometimes transgression can lead to more trust. Up to a point, of course. You don't want the system to kill a few people to find out that it has a certain normative framework. But I think there is something to this idea of those slight conflicts that can lead to increased trust if it goes well, but it can also lead to, okay, never again decisions.
Good point.
So Shane, you had a question?
Sure, this is, there is no right or wrong answer to this, but I've, for a lot of explanation systems I've seen and tried out, they're a lot of work to understand. And sometimes if you put in the effort, there's a big payoff. And I've seen in testing we've done with users that they, these are not highly paid users, but they like to take the easy route and not put in the effort. They may not be motivated, even if it may benefit them. And I was just wondering if, the easiness of the explanation may not be what people really need. I was wondering if any of you have any thoughts about this trade-off of effort, performance, motivation.
Well, I'd like to take umbrage with calling human beings lazy. I would argue that it's not lazy at all, but rather it's intelligent to minimize cognitive effort, to minimize time, and to minimize physicality. This is certainly what Simon said in his classic work, and also what we see in Zipf's principle of least effort. So I would argue that human beings are smart if they can minimize the amount of work.
I was talking about myself being lazy when I'm
well, I don't know if you're lazy.
System, so.
But I do think it's important to reframe the discussion and not consider that the humans should be doing the work, but whether we want to make the work accessible to humans. And that does mean reducing efforts of cognition, time, and physicality. I think that's really core to turn the discussion around the other direction.
I would answer your question, Shane, but frankly, I'm just too lazy to do that. I'm sorry. No, I'm just kidding. This is actually very salient in my line of work. It's a very high risk domain. It's very technical, and it has to be very standardized. Everything that we do in the military has to be something you can document, and it's very reliable because it's a very, very, very big organization, and we don't accept a lot of individuality. So we have to try to standardize things to the maximum extent. And so as a result, we kind of do build in a certain like threshold of cognitive effort for a lot of things, and systems that exceed that are not acceptable in the eyes of the decision makers. And I think that does it's part of my sort of persuasion to say, as a classic example from cognitive science, Gigerenzer as a result, if you want to try to explain probability, you can do so in a way that likely will be understood by most people by using natural frequencies, like say 3 out of 10 people who test positive for COVID-19, will get better, or whatever have you. Just 3 out of 10 is a natural frequency that most people can comprehend. If you say 30% as a result, they can interpret that a number of different ways, and that leads to some potential confusion. It's just a very old, very classic way of just the way that you present information has an effect on the cognitive understanding. And in a similar sense, there's also many different ways you can present information that either takes a tremendous amount of cognitive load or a little bit less. And so I seek solutions to this type of problem in some of these more, what I call low-level solutions, to try to minimize the cognitive effort, try to make something quicker to comprehend, quicker to learn even. You know, those are common goals in my line of work for that reason, because there are practical limits to like how complex a thing will be if it's going to be used. And again, most of my words are almost always motivated by this concept of usability and technology acceptance being the most motivation for me.
For me, thinking about cognitive effort in explanations, again, brings me back to the importance of audience. We've all experienced teachers, and some of us are teachers, who sometimes have a long-winded explanation and may or may not get to communicate to their students what this was all about. The best explanations are deeply thought through, in the sense that you know what your students do or do not understand, and then you really hit it on the nail with a very short explanation. You give them this one graph or this one piece of information or this one anecdote, and suddenly you create this knowledge. So effort isn't necessarily how much you say and how long you speak, but whether you can really understand and have a model of what the other one doesn't understand. And I think that takes a lot of effort, and it's not easy at all. And if you now want to build that into an AI, very difficult.
I have a question, actually. So there are humble people. Hello? I'm audible, right?
Go ahead.
Thank you. Thank you. So there are humble people who are not introvert, but they don't explain either. So what are the thoughts from the panel? Thanks, Dr. David.
Sorry, I did not hear that.
Go ahead.
Yeah, there are humble people who are not introverts, but they don't explain either. Like they keep giving opportunities to others. So what are your thoughts on that topic?
People who are not introverts?
Humble.
Yeah. People who are humble and are not introverts, but they don't explain either. So what are your thoughts on that?
Denise, looked like you were about to say something. Oh, okay.
I was going to say I couldn't hear.
Okay.
I'll stay humble and won't say anything.
Yeah.
Well, it certainly is important not to stereotype people and suggest that everybody thinks in the same way, or that everybody communicates and interacts with information systems the same way. And even though we have basic maxims or principles of how people interact with information, there's always wide variance within any population.
Thanks.
David, I think there are a few more questions. You probably see them too.
Yeah, beginning to. Georgi, you had a question?
Yeah, I just would like to get back to Eric made the statement that XAI for black boxes is futile, and I just would like to understand that what was the scope and the context of this claim.
Yeah, that's kind of a sloppy word for me to use. I don't really mean to suggest, of course, it's futile, but I think there's a lot of reason why the argument for more accuracy equals less explainability should be examined. There are a number of models that are intrinsically more capable that also produce similar or at the same level of results in terms of accuracy. And I think there's, personally, I look to the concept of good enough. You know, the QWERTY keyboard is not the most ideal layout of keys, right? It's something that was originally developed to slow down typists because the hammers would get all tangled up. But it persists today, even though we don't have the hammers anymore on typewriters, largely because we just accepted it. It was good enough. You could look at a number of models that have been trademarked, that have been developed, and actually are much more efficient, much more optimal. but they're not used because we kind of just cemented in things. And that's actually pretty much everywhere you look. This concept of like optimality, this quest for optimality is kind of an artificial thing. Even our own DNA. I mean, you can look at our own DNA and see a wide variety of redundancies that are not the most optimal design for encoding genes. And so I think there's a certain point at which I personally believe we've already arrived at which we can take what we've already got, and instead of keep trying to push the boundaries of accuracy, squeeze out 1% more of accuracy. And in doing so, now we're compounding the complexity and compounding the need for more and more and more explainability, and look at some more practical steps that we can say, let's make this thing more usable today as it is, as we have it right now. I like to think of continuing to push toward more accuracy as not unlike the strategy of, and we've got this pest problem, so we're going to introduce these snakes from overseas because they're a natural predator. And then a couple of years later, now we have a snake problem. So we're going to introduce, a weasel that's a natural predator of the snake. And then it turns out that they thrive. And now we have this infestation of weasels. And we just kind of keep compounding in things toward this, like in an effort to make something simpler in explanation, we make things more complex. And so futile, my mistake, bad word to use, I apologize. I just think that if we want to get something used, we want to see this actually benefit society in a regular person's life and really start to see the benefits that we all hope and dream about. I think we can do so in a lot quicker ways, a lot more practical ways than some of the approaches that XAI has embraced. That's the argument that I try to make.
So you mean that it's application dependent?
You're absolutely. I mean, there's certainly areas where you maybe the only model that's acceptable is like a completely black box model. I'm absolutely right. It's far too broad a field to really generalize too much. But I think the vast majority of the use cases that we like to talk about, like healthcare, for instance, is, in order to get doctors to use anything, you've got to really, really, really get on their good side. And to do so is going to do a lot. You're going to get a lot further with using more explainable models rather than trying to say, here's a really, really complex model and an even more complex explainer on top of that, and et cetera, et cetera, et cetera. Thank you. Very good question. I appreciate that.
Thank you very much.
Rosina, I see that you have a question. It reads, how convinced are panelists that lack of transparency of AI models leads to lack of trust?
I would say that varies by person to person. Some varies according to education level, context, and background. Some people do feel that there is trust in explanation. Other people feel safer when they don't know what's going on. I think it really highlights the importance of personal context and human variance. And that
I
goes
also
back to
think
the
it
idea.
matters whether we equate transparency and explanation or explainability. I think we don't care that much about understanding how and what machines are doing, and often not even how or what human brains operate. But you really do want to understand and get some explanations if a surprising behavior or output occurs. And I think it will certainly challenge my trust if I don't understand why it's doing it. Not how exactly, and I don't need a technical and a detailed sort of transparency, opening information, but I need something that gives me the answer to my question. Why is it doing it? What either are the person's motives or the system's goal or the system's target that is trying to maximize or optimize. If I don't understand why in that sense, I'm definitely mistrusting. But transparency, and this is why I try to distinguish between those two, transparency, if you accept the distinction, is much less worrisome to me. But inability to explain or inability to explain clearly, that's probably more concerning.
But why does not mean necessarily that it's the answer to the why is going to be on how the model works. you said maybe the goals, and the goals may not be from the opening the black box.
Yeah, I mean, the goal might be just one part of what's going on in the system. But if that's my main concern right now, I don't need to know the other things. But if, for example, the system has 7 goals and right now it has 1, and I don't know that it has 6 other ones that it may shift depending on context, then I might even get the illusion that I understand what it's doing. And I will predict that in another context, it will also pursue the same goal, but in fact, it will pursue a very different goal. In that case, lack of transparency, namely lack of knowledge what goals it has, even if it's only pursuing one right now, that could be costly. I might not know it's costly right now, but if I'm wrong and next time my prediction is incorrect, then I will also lose trust. So there's no sort of one answer, but I think at any one moment, we typically have a question and we hope to get an answer. And I hope that the answer also generalizes to a next context, but there's no guarantee for that.
Thank you.
Eric, did you want to add anything or?
Yeah, just really quickly, excellent question. So I did a pretty large systematic review of the literature on the concept of transparency for a paper some years ago. And I actually went well beyond computer scientists and AI, and I looked through, where does transparency come up? The majority of the places where that concept comes up is in politics and government and things like that. And so there's a wide body of literature that says pretty uniformly that the more transparency in those contexts equals more favorable outcomes. Your citizens are happier, they're more trustworthy, or they feel that government's more trustworthy. They express, longevity measures are higher. All kinds of great stuff comes from having a more transparent government. But in the human factors literature, we also have plenty of evidence that more transparency does not always equal trust. And in fact, in aviation, where I work, there are many times where we've actually had to make things more opaque intentionally because people got really scared or really uncomfortable with being shown just how uncertain some things are. And sometimes being able to see to that level does kind of make you a little less confident. There's a variety of cases where that probably is beyond just human factors, but that's the literature that I'm familiar with in this particular case. So I don't think it's an axiom that we can just, plant a flag on. I think in general, it's another one of these examples that Bertram mentioned earlier. It's kind of like we're all sort of talking about the same thing. Maybe we use different terminology, but I think in general, we want some level of ability to see in or understand, even if that understanding is not absolutely like mechanistic. I think that still leads to a sense of, okay, I can feel good about this. I understand what's happening. And that's the level at which I'm comfortable saying, yeah, I think that exists pretty much uniformly within the concept of machine learning.
So this may relate to the next question. This one from Harish. Harish, would you like to go ahead and speak up?
Sure, thank you. So Bertram had this slide where the question was, one of the questions was, why did the vehicle veer off the road, right? And we also said that differential equations might get us up to a point, but not past that point, right? So there are parts of the question that can be inherently solved by computational models, and then there are other parts which we do not yet have models for. Right, and this goes. So what Margaret was saying this morning, that we shouldn't expect the general public to come to us, but we should bring explanations to them. And this is just more of a reflection, and I don't know if it's an interesting question, but it's something I'm mulling over as to. Is the work in the social sciences and the cognitive sciences and even in HCI a problem of converting these really complex models that we do not understand yet into computational models that we can mechanically solve, and just moving that needle towards towards making automating more and more of generation of explanations. And I understand that we might never get computational models for some of these problems. There'll always be some residual things that need to be interpreted by humans. But I was just wondering if that's what it is. And I really liked what Adam's presentation today too. He talked about a grounded theory method and you know, a contextual inquiry. I did some of that in my previous life, but so I'm wondering if all of that goes towards building computational models.
I mean, in your chat, it seemed you were asking the philosophical questions. Are there some phenomena that cannot be represented in mathematical computational terms? Here, it seemed a somewhat more pragmatic question. You know, how far can we get with these models and get a certain job done? You know, have a sufficient outcome. I mean, the philosophical one is difficult, right? We have to recognize that mathematics is a form of representation, and there's no reason to believe that it represents all phenomena in the world that we can conceive of equally well. So, you know, our concepts are fundamentally vague and more vague in the human emotional relational domain. So the reason why love might not be turned into a computational model might not be because love, the phenomenon, is not modelable, but because the phenomenon itself is not even clear. And so the more we can actually agree on what the phenomenon is that we want to model, the better we can probably get a computational, mathematical, simulated, mechanical version of it. But it's gonna approximate what we want. You know, when we work on moral competence for robots, we're not thinking about building morality in the big capital M into the machines. We just say, well, let's talk about the components. Who did follow norms? Not just rules, but norms that have a community element, where it reflects what the community expects of it and not just its own goals. They can be actually in conflict. So you build small things and say, can we build a norm system computationally? You might not say that that's morality, and I'm saying, fine. I don't need to make the big claim. So I think it's sort of an incremental step, and the better we define our goals, as before, my argument would be, the clearer you are about the goals, the better we can work together to get the answer, the explanation, the computational model, the machinery. And the ill-defined goals are going to be, we don't know, did we succeed or not? That's just a very difficult question.
Thank you.
Yeah, I'll add, I guess, you know, in terms of the concept of like bringing explanations to the public, I know personally, I often think of this type of work that I'm involved in as similar to public health. You know, if you've ever lived in the deep South, you might be surprised driving along the highway to see billboards that say, don't sleep with your baby, or don't put a heater in your baby's crib, or don't feed your baby cough syrup. And there's all these signs are everywhere in the deep South. And I always found that very fascinating. I grew up in Massachusetts. So I said, where, you know, like, who doesn't know these things? But that's a public health message, because that's part of the idea, is getting the message out there to the people who need it the most in that sense. And so I do think there is an element of that where right now, the practicality of like what is being explained is based on, it's based on a high level understanding of mathematical principles that most people do not have. Most people do not handle probabilities well unless you've been specifically trained and you understand them. And so we've got to kind of make these things more for the lay ordinary person if they are to be really appreciated, or if we are to achieve the underlying goals of explainability in some way at some level, even if it's going to be for, say, regulators and auditors, so that they can make the rules that we can then feel comfortable. You know, like I haven't said it tonight, but I say it often, you know, there's a quip that says like, well, I don't know how a car works or how a plane flies, but I'm comfortable getting in them and using them on a regular basis. So again, we don't necessarily need this sort of mechanistic understanding. Not every single person will need that to be able to, say, work comfortably with whatever systems we have. but somebody will at some level. And I think right now what we have is only suitable, is only really beneficial to a very small group. So my sort of vision, the way I like to think about it, is a little bit more like kind of a public health message, like getting it out, getting it, making it more familiar. To that end, personally, I've actually taken groups of sailors in the Navy that have no understanding of machine learning whatsoever and brought them to the lab and run them through a whole day of nothing but familiarization with machine learning, just as like a STEM outreach. And if COVID weren't happening, the next step for that was to actually go out to ships and just kind of have this thing going on for that purpose. The more people are familiar with even just basic concepts of modeling and approximation and things like that, the more I think we'll get closer to like this concept of technology acceptance, which is kind of what I'm always geared towards. So anyway, very good question. I appreciate the sort of noodling of the topics.
Thank you.
Any other responses?
I did actually have something that I've been thinking about quite a bit, and it actually is something that, I think I can maybe tie back to some of the aviation examples that you did provide, Eric. So I was an aviator, and so I actually flew for a bit in the Air Force for several years. So when you mentioned the example of, having to intentionally make some aspects opaque because it could perhaps beget more cause for concern, then right away that, had me thinking about just, situational awareness and how, so I remember from the human factor standpoint that sometimes information would be intentionally contained within the flight deck if they were having to troubleshoot an issue from the mission crew, because too much of that information sharing again could, perhaps again, bring about that cause for concern. So how this ties back to XAI is, I know for myself, anecdotally, sometimes when I ask for an explanation, it's not based counterfactually. It's just to increase my situational awareness. So I'm curious if you've explored that or if there's been any thought put into explanation specifically for awareness.
Well, I don't have the most confident answer for that. I mean, there's not a lot of bridges right now between like the classic human factors world and the current like explainability domain. Although that's something that I kind of am always bringing in. I'm always trying to bring those things together, because if you pay attention to like human automation interaction literature, you see that if you don't get like explainability right in human automation interaction, then you get like a 3 Mile Island, or you get like a 737 MAX, or a variety of other of those types of conflicts that actually originate not from a failure in the hardware, but from a failure of the interaction between the human and the hardware. Often a misunderstanding of what's happening, and the human makes the results worse in their response. So that's like the classic human factors thing. I'm not aware of like studies that are specifically saying how does explainability improve situation awareness, at least right now. I am personally working on something with a large group from many different organizations, including NIST, the National Institute of Standards and Technology, and Department of Homeland Security, where what we've done is we've taken some framework from the intelligence community that basically was designed to improve trustworthiness of intelligence reports from the field. Because you didn't get to see like who was involved in this intelligence report, because they're undercover, they're out there in the wild, or in the cold, as they say in the IC. Because of that, there was a lot of distrust of the final product. I need to know who did this come from? Give me more information about this report before I'm willing to act on it. And that sounds similar, right? That's very similar to kind of the same paradigm that we're talking about here. So the intelligence community actually developed a set of standards that every intelligence report has to kind of meet these standards. And a lot of the standards are basically based in transparency. Where did the data come from? What's the chain of custody? And there's a whole series of them. So we actually have a call for proposals out right now to actually run studies where we use these standards, apply them to machine learning models and outputs, and then say, what are the effects on, say, things like trust or willingness to engage with, or maybe even situation awareness. That's kind of a future study that we're all planning on doing right now. But other than that, I don't have any, like off the top of my head, direct link there between explainability and, say, situation awareness personally.
Very interesting, thanks.
I invite Bertram or Denise to speak up if you like.
Just to say that it's important to understand when we're talking about information and trust, that for some populations, trust actually comes from avoiding information and information avoidance, particularly populations who are marginalized socioeconomically or otherwise. So when we're thinking about trust, information, and explainability, if we're trying to protect some of the disadvantaged groups, actually reducing information is seen as more comfortable and protecting. We don't ever want to think of people as monolithic groups and to make the assumption that we as intellectuals and experts love more and more information and to extend that to the general population and think everybody likes more information.
Yeah.
Sometimes good audience design means saying less or not trying to overwhelm them with information. Adam, your point about situational awareness, I think, highlights one thing that we often forget. And we even do this in our studies. We define a certain event, a behavior, an action, and we ask people to give an explanation, and we analyze that explanation, or we analyze how they communicated the explanation. But it's typically a single event. Whereas what you describe is a setting in which there's a dynamic unfolding of events, and you are checking in with the system, with your partner, with an expert, with your assistant, with your student, and you have this joint representation of what's going on. It's really joint situational awareness. And then these explanations are more like, where are you? Have you just done this? Why did you do this? Okay, you're doing this next thing. So you're actually having a representation over time of each flow of action and goals. And that's actually amazing. Like we are really good at forming these models and allowing a little flux there, as long as we know roughly where we are. This is fundamentally true for collaboration, right? We're fairly confident that we're going in the same direction. And if we veer off too much, then we want to say, oh, wait, did I not explain that? Or can you tell me why? So I think this actually, your example highlights nicely something that goes even beyond explainability. It's like the role of explanations in collaboration. And that is another step of challenge that I think with robots and AI at the current level of capacities, yeah, it's pretty difficult.
So I think that's all the time that we've got for questions right now. Thanks, Adam. I invite the panelists, if they would like to provide any final comments. If you have any, you're welcome to do so.
Just thanks for the questions, attention, and thank you to other panelists for your great comments. I enjoyed that.
Thank you.
Thanks, everybody. Remember the humans.
Yes. Eric?
Yeah, I really appreciate the opportunity to speak to everyone tonight, and the questions were excellent. Thanks for Pat for continuing to be Pat, who's always quick to keep me on my toes, and I appreciate that. And thanks for also to the panelists. I really appreciated both of your talks. I hope you guys are going to share slides, because I definitely have a lot to learn. So thanks again.
So I'd love to get your slides. Please go ahead and send them to me, or if you prefer, you can upload them in chat, whatever is easiest for you. And you're right, Pat, it turns us into ballerinas, and I'm looking for an explanation as to why, but I'm not sure I'll get one. So
don't try to explain, Pat.
Oh, yeah, you're right. Thank you. I need that reminder. So with that, bring close to the panel, and with my co-chairs, we're at the end now. So Sylvia and Prashant and Rosina, if there are things that you'd like to bring up, I'd love to hear them. I know one of the things that we'd like to say is that the proceedings are available on the website at this point in time. And I believe that there are some plans for bringing the video of the entire meeting online as well, but I'm not quite certain what the status is on that. Rosina?
Well, the one from yesterday is already available on our website. And the one from today, after all the processing, will be there as well. Also, I just created a channel for it in YouTube.
Thank you. Sylvia, would you like to speak up?
I would like to thank everyone for participating. It was really great. And I learned a lot. I see a lot of opportunities to discuss also more about the topic we open and do throughout the workshop. So thanks a lot, everyone. And thanks to the other co-chair for giving me the opportunities to co-chair the workshop with them.
Definitely. From my perspective, I saw Sylvia and Prashant put in an awful lot of work. And Prashant, you should probably get a last word here, given what time it must be at your location.
Oh, it's 10:45, but
oh, I see.
Yeah.
So you've been up since 2 or so. Got it. Okay.
Yeah.
Any last words, Prashant, you'd like to add?
Yeah, I really enjoyed the workshop. I think we had a terrific list of panelists and also invited speakers and also like presenters. So yeah, the discussion was very, very interesting. Like I think we achieved what we like set out for, like to get the discussion going. And yeah, about the videos and proceedings, I think are available, as Sylvia said and Rosina said, in the website. And also I want to thank Rosina and David for their guidance as well. Thank you.
Yes, Orzi stole my thunder because I was actually going to take some time to thank the 4 of you co-chair organizers, because I know this is not an easy task for this sort of distributed, across geographies and time zones, organization and facilitation. So thank you very much for doing this.
I appreciate your thoughts, Adam. So Rosina, you want to finish up? Anything else you'd like to say?
We have thanked the attendees, we thank the co-chairs, we thank the authors, we thank the panelists. We have not yet thanked the reviewers.
Yep, that's right.
And let's again thank our sponsor and
JP Morgan.
Yes, that's it.
So great. Well, with that then, any feedback with respect to the workshop, please go ahead and send it to us whenever you'd like. You know how to access us, and I'd be interested in comments from the audience, in part as to whether or not they'd like to see something like this at the next AAAI as well. So with that, welcome everybody to say adieu, and hope to see you again.
Thanks.
Have a happy.
Be safe.